Maybe if you could SMS or text your colleagues reminding them that we should gather here.
Because we're
I'm from the University of Warsaw, and I have the pleasure to chair the tutorial session of this conference. So I hope I have the pleasure to welcome all 130 of you, but I still have some doubts. So if you know that someone is still somewhere on the way, or is there someone stuck somewhere, or can we start, or should we wait another 5 minutes? No? So we have this year participants from institutions representing 8 countries. Obviously, majority of you represent Polish institutions, but during the school there are also people representing these countries. Sometimes one person, like for the Netherlands or Switzerland, these are the speakers of the tutorial session. We have today 2 lectures. After that, the barbecue dinner, which is as usually located in this wonderful wooden hut. So either follow the crowd, or you just go out from the building, then right and a bit up, and then you will find the location. Then you're welcome to join the after party, official one at least, in the Grota Club, so to socialize a bit more after the barbecue. And tomorrow we start early in the morning at 9:15, again with 2 lectures. Then we will have lunch and a hiking trip. And after that, please come here back, as we will have a tutorial session quiz with questions related to the talks. And the hike will be the same path as last year. We're hiking the Klimczat mountain with some beautiful panoramas over there. So we expect nice weather, actually perfect for hiking, around 20 degrees, sunny. So I hope there will be even possibility to see the Tatra mountains far away in the landscape. So that's quite impressive. And this is around 500 meters up and 500 meters down. Actually, the profile is very constant, boring. If it's hard for you to imagine how it looks, you can think of it as of a Lorentzian function with a full width half maximum of 2.5 kilometer and amplitude of 500 meters. And the last year we did the same path, but this was a bit tricky that everyone comes back to the hotel. And we actually did the right thing because most of you just at the midpoint returned back. So we were inspired by the quantum physics and spin physics properties, the famous spin echo phenomenon. So most of you did the right thing to return exactly in the middle of the journey. But some of you didn't follow the same path. So you ended up with some strange trajectory. And this year, please either memorize the route, make a photo, or go to the website. So on the website, you will have there is an app which you can download and you can follow the path. You can also use your favorite outdoor app, which is which reads the GPX file. The GPX file is available for download. You can make a photo now. That's the easiest way, at least to have any sort of orientation. Because you're responsible for your own. I mean, we cannot guarantee that we go together, but we cannot guarantee that you will stick to us. So you're responsible for your own to be back on time for the lecture, for the quiz tomorrow. So hike is relatively easy. You don't require very robust shoes. The path is rather smooth, so that's why we also choose this path. There are many ways to go up, but this is the one that is the smoothest one probably, and the trail is nice. And but still remember that these are mountains, so please remain responsible. Take enough water, use sunscreen, note the rescue number, or make a photo now. And again, please control the time to be back for the quiz. Questions during the quiz will be related to the lectures. We will probably use some online platform that you can access during the session with either your smartphone by scanning a QR code or going to a certain address, or with your PC. So please bring an electronic device. If not, then we will try to maybe print some copies for you as well. We will also divide you in teams, most probably. So the whole idea of quiz is not yet entirely finished, but we will most probably divide you into teams, and to foster collaboration between different institutions, you're welcome to create teams with as little people from the same institutions per team as possible to maximize cross collaboration between institutions. So you can already start doing, for example, the hike or now to try to find a team with people with the largest diversity. So people from abroad institutions, you will have immediately a lot of friends, I guess. And with that, I will just show you the outline of the hotel. So we will have the poster sessions here. Most of you know, under this roof, you go up 6 floors here, and then through a long corridor, and then to the poster session here. And we have also microphone duty, so please come to the people who are on this list. Please come to Jacek and Krzysiek before the session to get to know how the microphone works and everything, and show yourself also to the chairman so that he knows that these are you who are responsible. And first of all, thank you for this, for volunteering to take this duty. And as usually, we have the clean chalks, so they still have the same value. They are extremely robust, not sensitive to inflation. This is, again, one drink, so you can either invest and keep them for next year's, or use them on site. And please have fun, enjoy, and please learn something from this tutorial session. So you also get clean chalks for each question. This year, unfortunately, it is limited due to the budget. We can only give 5 clean chalks per lecture, per tutorial session lecture. This doesn't concern the regular lectures where you don't have clean chalks for question, but still I invite you to ask as many questions as possible. And let's get started. So we start with the talk from Professor Michał Baczkowski, who is representing Unipress, and representing is actually maybe not even enough to say, because he's the director of Unipress at the same time. So Professor Baczkowski did his PhD in 1995 in chemistry, actually material science. I was surprised by the title. This was something about burning gas, or?
It was combustion synthesis of aluminum nitrate.
Okay, so already related to nitrates. And then he moved after that to Warsaw to work in Unipress, to the institution that he's the director right now. And during his time, he devoted his work to growing gallium nitride. And he's also visiting professor at Nagoya University. And one of the, according to Stanford citation report, one of the two in the top 2% of the cited scientists in the world. And today he will tell us about the basics of growing gallium nitride. So, Professor, please.
Thank you. Thank you very much for a kind introduction. And thank you very much for inviting me. My name is Boczkowski, I'm from Unipress. May I ask you to sit here, the first row? Why you are sitting there? I would like to talk to you. I don't want to have the classical university lecture, you know, that I'm talking, you are sleeping. It doesn't make any sense. Okay. Hey, guys, come on. Don't worry. I would like to talk about bulk gallium nitride growth. I was asked to talk about it, and thank you very much for inviting me. Great honor, privilege, and pleasure. And now I would like to... Okay, this is the outline of my talk, because... Oh, some guys ran away. Okay, so... I don't want to talk about, I know you are physicists, so mainly I'll be talking about technology, but some physical phenomena will be discussed too. So this is the outline of my talk, and I would like to start from the beginning, so from the fundamental questions like why do we grow crystals, how can we grow crystals, and what does it depend on, driving force, yeah, I got this, I know. Here, and the key parameters regarding GaN crystals. Then we'll be talking about gallium nitride, okay? So, first question to you, why do we grow crystals? Why do we grow crystals? Yeah, but what for? Technology, so business, so you are money-oriented. Okay. Why do we grow crystals? What about you? Yeah. For the order. Okay. Well, any other proposition? Huh? So curiosity. Great. So I prepared this slide. The first point is curiosity. Do you know the story of liquid crystals? But you know liquid crystals very well, yeah? So, you know, 90 years ago, some people in the world worked on liquid crystals, and other people were laughing. It doesn't make sense to analyze liquid crystals. It is not liquid, it is not solid, it doesn't make any sense. And today, if you ask any kids, everybody knows about liquid crystals. Oh, I got a TV with liquid crystals, my laptop, my TV screen, everything is done by liquid crystals. So it was curiosity. The next example is aluminum nitride. You know, in 70s, Professor Glenn Slack, very good physicist from US, I had a great honor to meet him in my life. He built his own theory of thermal conductivity of solids, and he needed thermal conductivity of aluminum nitride. So he went to the lab, he crystallized aluminum nitride because there were no aluminum nitride crystals in the world at that time. He crystallized it, he measured thermal conductivity. 20 years after, some people well, nitride started to be very popular. People came to him and, hey, Glenn, let's do company. And today, one company, today this is Crystal IS, but Crystal IS belongs to Asahi Kasei, Japanese company. They crystallize aluminum nitride, they produce wafers of aluminum nitride, and they do UV laser and UV LEDs. So it was curiosity, but of course you are right, business applications, so we need substrates, we need epi layers for making transistors, Schottky diodes, lasers, LEDs. Also is ladies, this is something for you. There's no diamond, it's silicon carbide. Okay, so gel rail based on silicon carbide exists, and I found in the internet that some say that lab diamonds may be okay for cheap jewelry, but ask, do they truly signify love and romance? I don't know. So this is the question to you. I took this slide from the book of Peter Kapper from 2015. So 60% of crystals, they are semiconductors. So you work on semiconductors, as I understand. 12% for jewelry and watch industry. You know, watches are needed, so quartz. And other applications here are presented for crystals. Okay, so now we know that we can grow crystals from melt, from solution, from gas phase, and it depends on the properties of this material. Yeah? If we can melt some compound, we can grow from melt. But if we cannot, and you know very well this process from solution, this is salt, crystallization of salt, we can grow from crystals from solution. If we cannot grow from solution because we cannot find good solvent, we can grow from the gas phase, like silicon carbide. It's grown from the gas phase, aluminum nitride, gas phase. So we got silicon carbide feedstock material, and it is evaporated, and here there's the growth process. But still, so back to curiosity, because from silicon, from sapphire, the best growth method is crystallization from melt. But some people can grow crystals from solution. Sapphire is grown from solution. Silicon carbide is grown from solution. Even sapphire can be grown from melt. Silicon carbide from gas phase. Huge 8-inch or 12-inch crystals. So curiosity is in science, and everybody would like to determine, to study what they want to study. Okay. So driving force for crystal growth, supersaturation. And I try to find good definition in internet, and I couldn't. So everywhere that this is the non-equilibrium physical state in which a solution contains more solute than the equilibrium solubility allows at given conditions such as temperature and pressure of the system. Supersaturation is also used to describe the level at which the solute concentration exceeds, and this is, I think, exceed, this is the keyword, its solubility at given condition expressed as blah, blah, blah. Okay. And everywhere we can find such figure concentration as a function of temperature, and then we can analyze what happens when we dissolve a substance, a solvent at elevated temperature, a metastable state. This is supersaturation. I don't want to talk about it. Some examples. So this is gallium nitride crystal growth from solution under pressure. We'll be talking later about it. But we can see here gallium and nitrogen molecules, and nitrogen molecules dissociate on the gallium surface, and then nitrogen atoms are transported from the hot part to the cooler part due to temperature gradient here. And the concentration, equilibrium concentration here is for this temperature, but due to convection, concentration of nitrogen atoms here and here it's similar. So in this part, solution is supersaturated. Okay, it's clear, everybody knows it. So now, the question is, this method was very nice 20 years ago and 30 years ago for growing GaN. But then Japanese people add sodium for increasing solubility of nitrogen in gallium. So this is solution of gallium plus sodium, nitrogen under pressure, but there is no temperature gradient. So how supersaturation is created? Question to you. Any propositions? Yes. No, sodium increases solubility of nitrogen. So solubility of nitrogen in gallium is much, much higher than in this case. But there is no temperature gradient. The exceeded value, they are keywords. If you are talking about supersaturation, if you are thinking about supersaturation, think about exceeded values. Pressure. Here the pressure is higher than the equilibrium pressure of nitrogen for gallium with sodium and gallium nitride system. Okay? So you have to look for exceeded value. This is supersaturation. So in the supersaturation is that for us, for physicists, this is the difference of thermodynamic potentials at the interface between a crystal and its environment. That's all. I couldn't find it in the internet. I don't know why. I would like to ask ChatGPT. Okay. So now let me tell you a few words about key parameters regarding crystals. So habit. So if you grow crystal, then you can look at, okay, cubic, hexagonal, so you can see the shape of your crystal. I prefer this slide because there are a lot of crystals, and there are gallium nitride grown from 30 years ago in Unipress, and there are small hexagonal platelets. Today, boron nitride is grown, and it's boron nitride has the same dimension like gallium nitride 30 years ago. So maybe in 30 years you will have 4-inch, 6-inch boron nitride crystals. But habit is a first key parameter if we are talking about crystals. Then, of course, morphology. Morphology. So here I gave you the example of gallium nitride. Here you can see some steps and helics. There are a lot of helics. Here you can see only one helic on the entire crystal growing surface. If you see one helic on the entire crystal growing surface, it means that structural quality of this material is absolutely perfect, or almost perfect. So morphology is very important, and after habit, we have to analyze morphology. If we grow crystals on the seed, then we have to start from morphology. So morphology. Many people think that growth rate is the more important. No. Remember, morphology, structural quality, and then growth rate. And then properties of these crystals. Structural quality. So morphology, structural quality. And everybody knows X-ray diffraction. But does anybody work on X-ray topography? Nobody? Oh. So you can read it. This is from Lutz Kirsten, my colleague from Fraunhofer from Germany. And this is so nice technique. I don't want to talk about, rocking curves and then you can analyze your crystals and blah, blah, blah. But you can see all defects. All of them. Did you read it? Great. So, on macroscopic scale, look, everything. Such carrots, propellers, triangles, such, cracks, tiling, everything, and macroscopic scale, dislocations. So XRT, work on XRT. Forget classical X-ray. This is also classical Bragg reflection, of course, but, this is something new and something that give us more and more information. Of course, one of the methods for analyzing structural quality is to etch surface of your crystal. And this is the slide from Andrzej Szczerbakov from Institute of Physics. He's a very good grower from the gas phase. And if you must find a good etchant for surface. And then you can etch surface and see pits. If you see a lot of pits, you can count them. In general, they are related, they are correlated to threading dislocations, so you can determine dislocation density. Okay, growth rate, finally. Many people ask about growth rate. So growth rate is, everybody knows the rate of growth of a given phase in the direction normal to this phase. Okay. And this is the lens seed, gallium nitride. And then, it was grown, and finally we received hexagonal shaped crystal. And then if we destroy this beautiful crystal and analyze, all facets of the cross section, and then all facets, we can determine growth rate in each direction, in C direction or minus C direction, in non-polar direction, semi-polar direction. So this is growth rate. So I think growth rate can be understood very, very easy. Yes, please. In this picture?
Sorry. Yes, in this picture you have transparent areas of your crystal, and then you have like shaded areas.
No, this is, I think, the scattering of light, but this is not transparent crystal. It's amber crystal, and this is hexagonal shape because we started from the lens, and the seed was transparent, like you can see here.
Okay.
And then we received the hexagonal shape crystal, a few millimeters, 4 millimeters thick. So I don't think that it was absolutely transparent. I think amber color. And this features, well, they're transparent because we can see the grid lines. Yeah. But well, I cannot explain it. I don't know why. I have to ask my colleagues. Thank you for this question. We'll come back to this slide. Yeah. Okay. So now gallium nitride. So do you know nitrides? Anybody works on nitrides? One. Not a lot of people. Two. One guy from Unipress. Yeah. Okay. So, a very beautiful hexagonal structure, and there are three gravels. So gallium nitride, indium nitride, aluminum nitride, and of course, due to band gap, it can be applied. They can be applied for LEDs. So everybody knows LEDs, and LEDs business is based on gallium nitride. Recently, I met my colleague. I didn't see him 20 years or more. He's not a physicist, absolutely. And he told me, oh, I'm very happy that now the grain of sand, I said, okay, can give us a lot of light. I said, what are you talking about? It's not silicon. This is gallium nitride. In fact, gallium nitride with indium nitride. Of course, okay? Remember, it's not silicon. They are nitrides. And in 2014, three distinguished professors from Japan, Professor Nakamura, Professor Akasaki, Professor Amano received Nobel Prize for the invention of efficient blue light emitting diodes, which has enabled bright and energy-saving white light sources. So nitrides are applied, gallium nitride, indium nitride, aluminum nitride, and the alloys for general LEDs, general lighting, for lasers. I know Blu-ray, no perspectives for Blu-ray. It was a time that everybody thought that Blu-ray is the king, but today we know that iCloud won, so no Blu-ray. And this is the problem today with lasers, because we are looking for some application of laser diodes. I think it's in time we will find it. But high power, high frequency transistors. This also very in academic world popular, and many institutions work on transistors based on gallium nitride. You can buy a charger with gallium nitride inside. They are HEMT transistors built on silicon carbide, not on silicon, on silicon carbide, gallium nitride, gallium aluminum nitride. Okay, so there are typical devices. You can see here LED, this is UV LED, aluminum nitride or gallium nitride substrate, then quantum structure, quantum well, complicated. Then also this is laser diode structure, this is the HEMT transistor, two-dimensional gas is here, and this is the vertical transistor, like something like MOSFET. Everything, all these four devices, or kind of devices, are built on substrate. So we need substrate, we need native substrate, we need aluminum nitride substrates or gallium nitride substrates, so we need crystals. Because we have to crystallize gallium nitride, aluminum nitride, and we have to prepare substrates from crystals. There's a big difference, we'll be talking about it, between substrate and crystal. It's not the same. But before I got 3 slides about epitaxy, because I would like to tell you what is important in epitaxy. Okay, there are 1, 2, 3 things, and that's all. And if you know it, then you can grow epi, no problem. This is the structure of gallium nitride, and all these devices, what I presented you, they are built in C direction, on the C plane. Okay, we have also A plane and M plane, and you can see here the A plane is here, so it disappears. It means that the growth rate in A direction is the fastest. This is for Wurtzite structure, this is for gallium nitride. And here you can see the other planes, semi-polar, also used sometimes, but since there is no big crystal of gallium nitride, thick crystals of gallium nitride, so semi-polar planes or non-polar planes are not used very often. Epitaxy. So you know this process, of course, very well, and this is the, everything what can happen on the surface of growing crystal or growing epi layer. So the surface diffusion, adsorption, desorption, surface reaction, formation of cluster, insertion in kinks. But I think we would like to have such carpet, beautiful carpet, if we grow crystals, grow epi structure. And what is important? It was, I took it from Brian paper from North Carolina State University. The same surface morphology could be achieved either by changing the misorientation angle, okay, of our seed, which controlled the terrace width. So short terrace, long terrace. So this is misorientation. or vapor supersaturation, which controlled the surface diffusion length. This is the first rule for EPI, okay? So you have to remember about it. And then, for a fixed vapor supersaturation, a critical misorientation angle existed for the transition between bilayer steps and step bounces. However, this critical misorientation angle could be controlled by the vapor supersaturation to some degree. This is important because you would like to buy your reactor and have a reactor with push the button. So you push the button and the supersaturation is constant. Then you can play with misorientation of your substrate. But if you get the opposite situation and you get, the offcut is fixed, then you can start to change your supersaturation, so you cannot use push the button, and you have to work with your reactor to create the proper supersaturation. But this critical misorientation angle, then you can come back to the misorientation, can be controlled by the vapor supersaturation to some degree. So this is the mixing of them. That's all what you have to know about EPI. There are some examples. This is what we know to have, what we want to have. And there are some step bounces structure. Gallium nitride, melting point, extremely high. So we cannot grow again from melt. Temperature is not so high because silicon carbide or aluminum nitride is grown at 2,400 degrees C. But pressure, nitrogen pressure for congruent melting of GaN, 60,000 atmospheres. Today, impossible. So we have to grow from the from solution or from the gas phase, okay, according to previous slide. And the first method for grow gallium nitride was halide vapor phase epitaxy. This is grow from the vapor phase. This is it was in 1969. Maruska and Tietjen crystallized first gallium nitride on sapphire. The method is quite simple because this hydrochloride is flown with the carrier gas and reacts at 800 degrees C, let's say, with gallium to form gallium chloride. Then gallium chloride reacts with ammonia. Ammonia is flown here on this scheme to form gallium nitride. So there are two main reactions. Of course, there are much more reactions, but these two reactions are the most important. So, as I said, first GaN was crystallized in 1969, but they couldn't crystallize gallium nitride, in fact, of high quality. You know why? Because at that time, ammonia contained 1,000 ppm of water. So this gallium nitride should have contained, 10 to 20 or 21 oxygen. So high concentration of oxygen. Okay, so how to create supersaturation? Question to you. Are you sleeping well? Okay, so from the gas phase, we can create supersaturation, by the changing of pressure on the flow we are talking about pressure, equilibrium partial pressure and real pressure of gallium chloride. At ammonia-rich conditions, this is for creating supersaturation in such system. So the first key parameter, habit and morphology. Morphology, I already showed you. One hillock on the entire crystal growing surface. This is crystal from Unipress. Habit, if we grow, this is crystal from Mitsubishi Chemical, and if we grow thick material, there is formation of side facets, semipolar facets, you can see here. So this is something like habit of this crystal. And if we grow, if we put the seed to our HVP reactor, then we start to grow. Of course, it's like in epigrowth, there's formation of steps at the beginning, but we would like to grow thick material so that there are macro steps. But in time, source of macro step disappears. And C-plane, because we grow on the C-plane, you remember the slide with the planes, C-plane is recovered. And then we can observe formation of some hillocks. So there are steps, macro steps, and hillocks. And then, you can see on the surface of your crystal, you can see some macro steps, and many, many hillocks. But hillocks consume each other. So finally, you can see a few hillocks or 2 hillocks on the entire crystal growing surface, and finally, 1 hillock on the entire crystal growing surface. So this is time, in time, what we can observe during the growth. Structural quality. So structural quality, of course, in HVPE, it depends on the seed used. So if we use high quality seed, we can keep structural quality of the seed. You can see here the data from synchrotron wide beam back reflection X-ray topography against Lutz Kirste from Germany, and this uniform gray contrast indicates a high degree of crystalline perfection. If we use sapphire, then we are in trouble because we can see plastically deformed crystal. So in general, if we know how to grow, we know how to control supersaturation, then we can, if we have high quality seeds, we can grow bulk crystals, gallium nitride crystals by HVP. If we have sapphire, then we are in trouble because crystals are bad quality, plastically deformed. Of course, rocking curves, classical rocking curves for high quality material. I would like to skip this slide. Selective etching. For gallium nitride, KOH and NaOH solution is quite good. So if we etch surface should be prepared to the epi-ready state, then we can find pits. And we can find small pits, and believe me, they are related to edge dislocations. It was the study with TEM to correlate pits with dislocations. Average in size, they are mixed dislocations, and big pits, they are related to screw dislocations. So this is very nice technique for analyzing structural quality, very cheap, much cheaper than X-ray and XRT. Growth rate. Growth rate is high in HVP, it's higher than 100, 200 microns per hour, no problem. But you can see here, for example, that the growth rate, I said the growth rate depends on partial pressure of hydrochloride or gallium chloride. But you can see here that for same value, increasing ammonia, we can increase growth rate. So it's not so easy to determine the dependencies of growth rates, even if we got only gallium chloride and ammonia, okay? So still we can play with ammonia flow and with hydrochloride flow and increase growth rate. But growth rate is not so important. Crystals like to be grown slowly. Remember about morphology and remember about structural quality. This is data because for growth rate depends on this carrier gas because we prepared some semi-polar and non-polar substrates, so we can measure growth rates. It's easy. Okay, incorporation of dopants in HVP. Incorporation of dopants, for typical HVP, we can observe silicon because we use quartz reactor, and the carbon. There's no carbon because if we do not put graphite to the reactor, there's no carbon traces in HVP, and this is very important. Oxygen, close to 10 to 16th, That's all. Fujikura from SCIOX, they prepared quartz-free reactor, and then oxygen, carbon, silicon, they were below detection limit of secondary ion mass spectrometry. So finally, free carrier was 10 to 14th. So high purity gallium nitride can be grown by halide vapor phase epitaxy. Of course, we can dope because for application we need doping, and we can use dichlorosilane or silane for growing N-type gallium nitride or germanium tetrachloride, and we dope with silicon, we dope with germanium to obtain N-type, or we can use iron, manganese, or carbon to prepare semi-insulating gallium nitride by HVPE. It's also possible, and the manganese is the best. Look here, the resistivity is extremely high, and manganese is the best dopant for obtaining semi-insulating gallium nitride. There is no relation to spintronics, okay? One example, N-type HVP gallium nitride doped with silicon, and we observe that if we increase silicon concentration in our crystal, we see that free carrier also increases. It's okay, it's linear dependence, but suddenly we see compensation knee. So silicon concentration in GaN increases, but free carrier concentration decreases. The question is why? I got a lot of time. Excuse me? No? Okay.
Does it start to substitute the other atom?
Yeah, but I would like to add that there is, during this growth processes, we didn't add any other elements. So this is only silicon, gallium, and nitrogen. So what happens? Okay, you know, physics is, very beautiful, but sometimes complicated. And if we would like to create N-type in semiconductors, then even if we do not add any atoms, only this donor, only one donor, the silicon, then there are formation of acceptors, like gallium vacancies. So when we saw this curve, we knew that, okay, for strongly N-type material, there is formation of gallium vacancies. Gallium vacancies acceptor in gallium nitride. So we were sure that this is compensation effect by gallium vacancies. We measured yellow luminescence, and we knew that yellow luminescence is also related to gallium vacancies, and this yellow luminescence, intensity of yellow luminescence increases with increasing of silicon. Okay, we're sure, there's no doubt, if we dope silicon with higher concentration, we create gallium vacancies, because formation energy of gallium vacancy is very low. If Fermi level is in the conduction band or close to conduction band, easy. Then we found a paper from North Carolina, and it was written and analyzed that in aluminum nitride with silicon is the same effect, compensation knee, due to gallium vacancies. Okay, so we're very happy. We published this data. And then sent samples to Philip Tuomisto to Helsinki to positron annihilation spectroscopy measurements. And he said he can see by PAS gallium vacancies. And Helsinki told us there are no gallium vacancies, completely. Huh? So, and they proposed that this is autocompensation of silicon and the formation of silicon-silicon complexes. And this is still open question for physicists. We get samples, if you have any ideas, to analyze it and to solve this problem. Because I don't believe to Philip's explanation. I'm co-author of this paper too, but I don't feel it very well. I would prefer these gallium vacancies, but they do not see gallium vacancies. So this is open. Sometimes we have the problem. Okay, so I said that we can grow by HVP thick gallium nitride, so you can say, okay, so it's easy. If you can good seed, you can grow gallium nitride, thick material, we got crystals, we can prepare substrates, everything, we are home. Troubles. Anisotropy of the growth. You know, this is the seed, high quality seed. We'll be talking about a monothermal method. This is high quality seed. This is gallium nitride HVPE, halide vapor phase epitaxy grown in the C direction, okay? And this is part grown in lateral direction. And we can say, okay, no problem. We can increase the size of our crystal. But the problem is that if we measure by SIMS concentration of silicon, oxygen in this part of material, this is low, as I showed you. But in this part of material, oxygen is extremely high. It means that if the crystal is grown in lateral direction, there's different incorporation of dopants. If we have different incorporation of dopants, what can be expected from structural quality point of view? Different lattice parameters. And in fact, lattice parameters here are different than lattice parameters here, because there is different incorporation of dopants. We calculated it knowing X-ray data and incorporation of dopants, and this is the calculated stress close to the edges of the growing crystal. So if the stress is too high, some cracks can appear, and then we cannot grow thick material because this material is cracked. This is measured by Raman. You know, the stress is generated close to the edges. So this is the main problem. And of course, there are the model of the growth looks like that we got seed, and let's say that a parameter of seed is higher than a parameter of deposited layer. Okay, possible. So then we have this strain here. And seed is under compressive stress, and the layer is under tensile stress, okay? It's clear, I think. But they are wings. And the A lattice parameter of wings is much, much bigger than A lattice parameter layer. So the seed is under tensile stress and compressive stress, but the layer is under tensile stress. So for some critical thickness, it's cracked. And therefore, we cannot grow thick material in HVP. Of course, there are some tricks, like put the metal around the growing crystal to dissociate ammonia and decrease supersaturation to zero close to the edges. And then we do not observe the huge growth in the lateral direction. But still, we cannot grow really thick material thicker than a few millimeters, or 5 millimeters. okay? There are two derivative technologies for HVPE. One is halogen-free VPE, developed mainly in Japan. Yes, please.
Yes, so I want to ask, what is the reason for this higher oxygen incorporation in those sites?
This is a very good question. If I say that this is a very good question, it means that I do not know answer for it. So this is a very good question because in all methods you will see we observe the same. So in growth in C direction there is no huge incorporation of oxygen. In semi-polar and non-polar direction there is huge incorporation of oxygen. It happens in sodium flux method, in a monothermal method, and in HVP. This is like the property of gallium nitride. This is the same crystal in the reactor. It's not like that this is the next process, a different process, and I put more oxygen. No. And on the C plane, we do not see a lot of oxygen. Oxygen does not build to the C plane, on the C plane. But yeah, it's like something like polarities. Yeah, this is probably the reason for that. Yeah, thank you. So coming back to these technologies, this is halogen-free VPE. There is no HCl. HCl is corrosive, so there is no corrosive environment. Growth rate is reasonable. Purity is reasonable, developed in Nagoya University and Toyota in the lab. We have to keep gallium at higher temperature, close to 1300 degrees C. This is difficult for quartz. And OVPE. Then water is flown, vapor of water is flown over gallium. And gallium oxide is formed, and then gallium oxide reacts with ammonia to form gallium nitride. Then the crystals are completely black, and they contain a lot of oxygen, 10 to 20. Free carrier concentration is extremely high. Low resistivity, 10 to minus 4. This is what people need for preparing, vertical transistors, for example. So as low resistivity as we can obtain. So this is the second technology. Without big success because halogen-free VPE and oxide VPE crystals are not sold, so still in the lab. Okay, now I'd like to tell you a few words about high nitrogen pressure solution growth. It was the first method that gave us possibility to obtain monocrystals of gallium nitride in 90s, and I already presented you this method. This is 1 centimeter square platelet with dislocation density 10 to 2. High quality gallium nitride, big success of Unipress. And then we couldn't grow bigger material. So we started to work with seed configuration or multi-feed seed configuration when many seeds were placed in the crucible with gallium between them, temperature gradient was applied, and then we dissolved the seed from the bottom side and grew the crystals on the top sides. It looks like that. So we transferred these bad quality seeds from HVP, from sapphire, to high quality seeds from high pressure. And we crystallized these small crystals up to 1 centimeter square or even 1 inch. And we prepared substrates from them with epi-ready surface, and we demonstrated laser on that, but it was too complicated for us, and we stopped this technology. We stopped this technology, but when this technology was on top in the world, then Japanese people said, okay, Polish people had a lot of problems because the solubility of nitrogen in gallium is very low. So they add, I told you that, sodium to gallium to increase solubility of nitrogen in gallium. And they started to grow gallium nitride, also of high quality, small crystals. But Mori Sensei, who was one of the the sodium flux method started in Sendai by Professor Yamane, but then was transferred to Osaka, and Mori sensei started to work on it. And Mori said, I do not have any time. I would like to grow crystals faster, big crystals. I'm not interested in such small crystals, even of high structural quality. So he introduced, point seed technique. This is sapphire with gallium nitride point seeds. So the MOVP grow through the mask. And then in sodium flux method, the seeds are overgrown in lateral and vertical direction to obtain the bulk material. So these point seed techniques work, and Mori demonstrated 4-inch, 5-inch, and 6-inch gallium nitride by this point seed technique plus coalescence of the small seeds. And coalescence must be done in M direction, in A direction, A. If we do it in M direction, there is the problem. Okay, but they were not happy with these crystals, and the crystals demonstrated some cracks, and they started to analyze why. So they found the oxygen concentration and lattice parameters here in the sector grown in C direction is different than here in the sector grown in lateral direction. Same like in AGP. That's what I told you. So the stress was generated. So they said, okay, so we have to grow again. We have to start the growth from the seeds, point seeds, but then we can switch 3D growth mode to two-dimensional growth mode. It was a goal. But how to do it? And they analyzed, supersaturation, temperature, habits, morphology of the growing crystals. And finally, they started to grow crystals by sodium flux in this manner. Imagine that this is the reactor. So this is nitrogen pressure is everywhere. It's not so high. It's not 10,000 atmospheres. It's 50 atmospheres up to 100 atmospheres. And this is the point seed, the sapphire with gallium nitride point seeds. And this seed is in the solution. So the pyramids are grown. Okay? So then, under pressure, this seed is pulled up from the solution, and the solution, gallium and sodium, which is here between pyramids, reacts with nitrogen. So we have lateral growth only in lateral direction, no in C direction. But of course, there is a small amount of this solution between pyramids, so they have to pull up this seed again and again and again, faster. And finally, they can grow crystal in two-dimensional growth mode. And only this material, this one, is good for preparing substrate. This one is to trash, and this one is good. Morphology. This is morphology. HVP looks better. No one hillock. But if we slice this two-dimensional part, it's transparent crystal. And the quality is quite good, even if they start from sapphire, because these locations are, they form bundles. They form bundles. I thought at the beginning they have to be bent. It is well known in epi, but they create bundles and they are propagated as a bundle, and then they are annihilated. So dislocation density is lower in this two-dimensional part, and according to rocking curves, quality is quite good. Of course, you can ask about growth rate. They never publish growth rate. This is very, very often in our job. We don't want to publish everything. But if you take some part from the papers, this growth process lasts close to 300 hours. So growth rate is close to 10 microns per hour. Purity. This is not SIMS, it's thermal conductivity. It's thermal conductivity as a function of temperature for sodium flux crystals. And you can see that at low temperature, it's the highest value. It means that the purity of this material is really high than HVPE. At room temperature, what is important for devices, it's very similar. Even HVPE is higher. But at low temperature, sodium flux looks the best, so high purity material. Do you know something about thermal conductivity? Thermal conductivity, yes. So why diamond is the best thermal conductor? Physicists. Because I understand copper. There are a lot of electrons and the thermal conductivity is extremely high. What about diamond? Diamond has higher thermal conductivity than all metals. Why? No! Easier!
High quality?
Huh?
High quality?
No, but the copper is also high quality. Oh. Do you work on solid state physics? Have you ever heard about phonons? I think. Yeah, thank you. And what is the next question? Here this is the T2 minus 1 relation, yeah? And this is, we can say that there's, the phonons are responsible for thermal conductivity. Which principle of conversion with principle of how much? Guts? Zapomniałem słowa. Zachowanie.
Energy conservation.
No energy conservation, but what principle of conservation is broken? Sorry, it's my Alzheimer. Huh? Momentum. Yeah. And what kind of in the first Brillouin zone? Yeah. Have you ever heard about umklapp processes? Yes? So please read about umklapp processes for phonons. Okay, so Mori with sodium flux prepared 6-inch gallium nitride, high quality, and they started to use these seeds for growing GaN by a monothermal method. They said that this is not, sodium flux method is not the best method for growing, for doing mass production, okay? But this is very good method for producing seeds for other methods. Why a monothermal? Because in a monothermal method, Mitsubishi, I showed you here that it is cooperation between Osaka University sodium flux with Toyota Gosei sodium flux with Mitsubishi Chemical, a monothermal method, because Mitsubishi is a leader of a monothermal method, and they can crystallize by a monothermal method huge crystals, 4-inch, high structural quality, but they need seeds. So they started to cooperate. Japanese are crazy on gallium nitride. So, few words about a monothermal method. This is the grow from solution, and you can see here the...
Do we want to make a break, or you?
Or if you want to have...
Up to you and up to the audience, so I leave.
Up to the audience. You want break, or you don't want to have break?
Or we continue straight and after the lecture, so that's...
Your decision.
So I think they're waiting for coffee, so I think we go without the break.
Okay, thank you.
But if there are any questions, maybe because we traditionally also ask questions during the break, there were already some questions, so you can also ask during the lecture, but maybe if you have other questions, then it's also a good moment.
Slide, I think 54 or something, you present method, Unipress method for growth.
54.
I think it was 54 or something like this.
Okay. Unipress, yeah. Continue.
Yes, sorry for that.
No.
Maybe previous slides. Yeah, this simulation, I think. Yeah, so as you show us I don't know if I understand correctly. Is there any like self-termination process in this growth? Because as I understand, you use some small single crystal, yeah, on the center here, and then as I understand from this simulation, the growth on the sides is much bigger than in the
yeah, I transfer, well, this is simulation, but I transfer, we used the HVP material as a seed, so they are crystals, okay? The stock of the crystal. Gallium is between them. We dissolve the crystal from the backside, nitrogen side, so therefore, there is nitrogen in the solution, in gallium here, okay? And then the growth is on the top side of the crystal.
Oh, okay.
Okay?
Okay.
So this is the trick. But in time, we grow here and we dissolve from the backside the seed. So finally, we can transfer even whole seed or almost whole seed. Then we have to polish to remove seeds completely. But we transfer, we dissolve the HVP material and we grow high pressure material.
Okay, I get it.
It was the idea.
Yes, so I would like to ask about this improved by Japanese sodium flux method. I hope that it's not a very stupid one, but I was wondering if these pyramids that they were, observing, they were macroscopic enough so they can observe it, with like their eye, or how do they know that these pyramids are there?
How they were observed, these pyramids.
Yeah. Mm-hmm.
Yeah, but firstly, when they grow crystals spontaneously, they observed that the pyramids can be built for some temperature pressure conditions, and then they stop the growth. They prepare seed with many seeds, point seeds, and then they stop the growth process and they observe the pyramids.
Okay,
then they also observe pyramids by TM.
So they checked how to grow pyramids and...
Yes.
Okay.
Yes.
Okay.
One more question.
So sorry, but you mentioned this oxygen contamination especially on this lateral growth, and was it the source of the oxygen was from the water? Yes, or from the
water
ammonia,
only in vapor in the OVPE, so oxide vapor phase epitaxy when we use water. But no, this is not from water. It's in the system in HVP from quartz, in sodium flux probably from the crucible, from the elements of reactor.
Okay, so
this
it's
is the
not
source
very
of oxygen.
Obvious source, but very many of them.
But everywhere you will see also in ammono, distilled oxygen is the most important dopant.
Okay, thank you.
Okay, so there are no more questions. Then I think we can continue.
Okay. So we are here for ammonothermal growth, and they are in the autoclave, high pressure autoclave. There is ammonia under pressure, a few thousand atmospheres, and there are crucibles with gallium nitride feedstock polycrystalline gallium nitride. And this feedstock dissolves in ammonia and is transported by convection to the second zone, where seeds are placed and crystal growth takes place, because here solution is supersaturated. There are two ammonothermal methods, because we have to use mineralizers for increasing solubility of feedstock. And if we use alkali metals, then we can talk about basic ammonothermal method. And then the feedstock is kept in the lower temperature because solubility at lower temperature is higher. We call it retrograde solubility mode. In case of, if we use halide compounds, then we are talking about acidic ammonothermal method. And then the seeds, the feedstock is placed at higher temperature because solubility here is higher, and the material is transported to the lower temperature part where seeds are placed and crystal growth takes place. So there are two methods, and this one, acidic, is used by MCC, Mitsubishi Chemical, and basic is used by Unipress today. Before was used and by some other companies like Kyocera and 6Point. Ammono in Poland was created at the Warsaw University in the end of 90s. Then was they created company, Ammono company, and they grew crystals by ammonothermal method. They cooperated a few guys from university and they created this company. They cooperated with Nichia Corporation, huge company, Japanese company. They created a factory. Then they were in trouble, in bankruptcy estate, and finally Unipress bought from the court this company, and from 2017 we developed basic ammonothermal technology. Okay. So this is the temperature time profile for ammonothermal growth process. You can see that at the beginning, feedstock is this higher temperature, seeds are at lower temperature. This is backcatching process. So we'd like to couple the seeds with the solution. Backcatching is very important. Without backcatching process, there is polycrystalline growth. So we have to have this backcatching process, and then we have to switch temperature profiles, and now seeds are at low temperature and can be grown, and the feedstock is at lower temperature, is dissolved in ammonia, and then this part lasts 2 months. So the growth rate is very low. So we are like in agriculture, the crystals are grown and we are sleeping. There are some crystals, 2.2 inch and 1.2 inch. They are crystals. This is the technological room, technological hall with autoclaves. There are 12 autoclaves today. We are still placed for 4 autoclaves. So if you'd like to visit us, please call me, and the Ammono, this part of Institute is open, and you can visit ammonothermal growth lab, and we will explain you everything what is needed. So the idea of this growth is like that it is the slender, and the slender is to overgrow lateral direction. If we can slice this rectangular shape, we join it with the second rectangular shape crystal. So we use tiling technology. In tiling technology, the very important is this. There are 3 angles, alpha, beta, and gamma. The angular differences of these angles are smaller than the variation of crystal offcut. So the tiling seam then that does not disturb the epiflow during the epitaxy. This is very important, and we know it. We got this technology. Then we increase the lateral size of this crystal, and if we can enter the circle 2 inch, then we can slice, or 2.2 inch, then we can slice the round shape crystal. Then we can prepare substrates, or we can grow again on the round shape crystal. I will tell you in a few seconds why we prefer round shaped crystals than hexagonal shaped crystal. first seeds, there were HVP material from Nichia company, bad quality, EPD, edge pit density, when we etch surface with high threading location density, 10 to the 6. Rocking curves, not very narrow. History, because there are some people ask how it looked in time. So they use HVP material, an overgrown lateral direction. But still, the part which is grown in C direction, in minus C direction here, was not so high quality. This part, lateral part, was high quality because crystals was nucleated on the edges, and this is almost defect-free material, believe me. So what was done, they prepared the new slender from this part, which was grown laterally, and it was overgrown in lateral direction. Now there is no difference in the defects. And then they started to increase size, they started to join crystals, they started to do tiling technology for obtaining bigger material. So it was like that. And of course, if we analyze again, like in case of HGPE and sodium flags, if we grow on hexagonal shape seed, then we can observe some cracks. And we can observe that there is the different incorporation of dopant here on the M facets and on the minus C plane. So different incorporation of dopant, different lattice parameters, stress, cracks, relaxation by dislocations, crystal to the trash, not for preparing substrate. So what is done in Amono today? We use some metals for blocking growth in the lateral direction. Of course, if you'd like to grow in lateral direction, there is no metal border. But if we don't want, we build borders from silver, and therefore we prefer round-shaped crystals because it's easier to build this border. But the top secret is here, that the height of the metal border is like the height of the new grown material. So there is no possibility to formation of the M facets and different oxygen incorporation or acceptor incorporation of this lateral facets because there is blocked. So this is the trick, what is used, and therefore we prefer round-shaped seeds, and this is how it looks after the growth process. So this is they are our seeds. Okay. Mounted on the metal plates. On the metal plate they are mounted, and then to the crystal growth zone, and you can see the final result. There are metal foil around each seed. And the height of the metal border is like the height of the new grown crystal. Of course, very important thing is convection, and we analyze convection flow in our autoclaves. And it is very good for, because it's cheaper to analyze in the computer and then change the configuration, crystal growth configuration for obtaining, laminar flow. We see that turbulent flow is not the best solution for growing our crystals. And morphology, according to our key parameters. So there are macro steps and hillocks on the entire crystal growing surface. And here I would like to, I need some data from XRT. Because by XRT, we found some propellers or carrots. Lutz Kirste found by XRT, and he said, okay, there are defects with a different lattice parameters, a little bit different lattice parameters in these triangles. And then we correlated this result with the result what we can observe in UV illumination, different color. So different color, different incorporation of dopant, different lattice parameters. Easy. So then we started to analyze morphology, and my colleague Tomek Sochacki spent a lot of time to analyze the interaction of hillocks in ammonothermal growth. And there is no problem if these hillocks are side to side positioned parallel, for example, because the steps are flowed only in M direction. 60 degrees only in M direction. But in case of, for example, then these hillocks are positioned at angle of 120 degrees, then the steps can be formed and flown in the A direction with the fastest growth rate. So incorporation of dopants is different. And therefore, we can create these triangles with different color or different lattice parameters because the growth rate is different, incorporation of dopant is different, so lattice parameters are different, and the small stress is generated in crystals. So you can ask, what is the solution for that? In Ammono, when we can place close to 100 seeds in the autoclave, it's not one crystal when we control the morphology and everything. There is the crystal growth zone, huge autoclave, 100 seeds. So we think today that the solution is to prepare lens seed, what I showed you at the beginning, and then immediately create one hillock, and then grow crystals with one hillock. Then there is no hillock interactions, there is no formation of the Scarrott's defects or propellers defects, and then crystals is of higher structural quality. So this is something for us for the future to do that. Structural quality of Ammono is extremely high, what I showed you at the beginning. So EPD is 10 to the 4th, very narrow rocking curves. And now XRT again. This is XRT in back reflection mode. And you know what? Growers are very happy. Nothing. We crystallize perfect crystals. And you can find such pictures in many papers about silicon carbide, aluminum nitride, other crystals. XRT in back reflection, and people say, we are the best. We grow crystals without defects. Don't do it. The same crystal is XRT transmission mode. You see the difference? So if someone shows you XRT back reflection and say, oh, you know, my crystals are perfect, ask him or her, show me XRT in transmission mode, okay? So XRT is very nice technology for analyzing defects and for determining defects in crystals. Kirste found Bormann effect. Have you ever heard about Bormann effect? Someone who works on X-ray? So this is dramatic increase in transparency for X-ray diffraction in transmission mode. Found in 1942, I think, by Professor Bormann. And you can see all defects, dislocations in material. If you take commercially available gallium nitride from HVP grown on sapphire, there is no Bormann effect. Nothing. So the quality is bad. In case of Ammono, the main donor is oxygen, and therefore the crystals are highly conductive. If we compensate oxygen donors by manganese acceptors, then we can obtain semi-insulating material. And there are some information, we have some time still, okay, from positron annihilation spectroscopy for highly conductive crystals. There are a lot of gallium vacancies, what I told you. The Fermi level is high, there's formation of gallium vacancies, they are acceptors. And there are vacancy hydrogen complexes in Ammono. And these results are well correlated with photoluminescence. So Reszczikow measured photoluminescence for ammonothermally grown crystals, and he showed that UV is related to magnesium, blue luminescence is related to zinc, yellow luminescence, they are complexes of gallium vacancies with hydrogen, like positron annihilation spectroscopy said. Orange luminescence is the same. This is unknown, but we expect that this is the same. Red luminescence, it's also the gallium vacancies with oxygen. If we anneal ammono at high temperature, then intensities of some luminescence peak decreases, and intensities of some luminescence peak increases. So it is related to dissociation of defects, according to Reszczikow. And if we grow on ammono epilayers, this is our ammono with dislocation. This is dislocation line. After the growth process, you can see that this is helical dislocation here. It does not transfer to the epi layer, but in ammono bulk, this is helical dislocation is formed. After annealing during the growth process, epi process at 1100 degrees C. Now you can see here that this is not transferred to the normal line of dislocation is transferred to the epi layer, but in ammono bulk is helical dislocation. An explanation of this phenomenon is migration of gallium vacancies. So there are a lot of gallium vacancies at high temperature. They can migrate to dislocation line and create helical dislocations. It calls Cottrell atmosphere. Have you ever heard about Cottrell atmospheres? This is the last chapter in Kittel, I think. So therefore you don't know it. But this is the Cottrell atmosphere, so formation of the like void, like empty space close to dislocation line, so helical dislocation. And this is well-known effect in metals and also in silicon gallium arsenide and in gallium nitrate. But this is related to this data from Reszczikow, when he observed that some intensities of some luminescence peak decrease and intensities of some luminescence peak increase. So the intensities of luminescence peaks from the related to defects, vacancy, gallium vacancy with oxygen, gallium vacancy with hydrogen, it means that there were more gallium vacancies in the system, in the crystal, and they transfer to the dislocation line. So it was Cottrell atmosphere, and that you can expect in highly conductive gallium nitride, such helical dislocations. Now, very important thing. I said at the beginning that there is crystal and there is substrate. This is crystal. From this crystal, we can prepare substrate by wafering procedures. Don't forget about them, please, because the crystal must be sliced, misoriented, drilled, the grinding is needed, lapping, mechanical polishing, chemomechanical polishing, cleaning, many operations. And then you got substrates. The crystal is after, with your morphology. Substrate is epi-ready, or one surface is epi-ready. So this is for silicon. I found it in the internet. How many operations must be done, from the Czochralski growth process by slicing, beveling, lapping, etching, heat treatment, polishing, cleaning, inspection, packaging, shipping, and sending an invoice. Yeah, and then you are waiting for money. So same must be done for gallium nitride. So we can grow by ammonothermal method crystals. Then we have to prepare by wafering procedure, machining procedures, substrates, or next seed, and some crystals come back to the autoclave, and this is the process. And, you know, we have to find the M plane, we have to find C plane, we have to do slicing, you know, this is, it works? No, it does not work, but okay. But we have to slice for the platelets, then we have to drill, we have to prepare primary flat, so this is M plane, secondary flat, A direction, to show A direction, M direction, M direction, A direction. So all these procedures are needed, then lapping, mechanical polishing, and CMP for preparing epi-ready surface. Even after, you know, optically flat, if you see optically flat surface, there are many scratches, and the RMS is too high for doing epi. So CMP is absolutely needed. And you can see here an example. This is, we finished the surface with the diamond grains, diamond slurry, 50 nanometers and rocking curve. 6 hours plus 6 hours of CMP and the rocking curve is narrower. And then you got this carpet, what is needed for epi growers. Without this CMP, there is subsurface damage, and at high temperature, scratches can be visible, and the substrate is to the trash. Not to the trash, we have to prepare surface again. So this is good surface. And there are our substrates that are, we sell them. So we sell high carrier concentration and N plus type with 10 to 19 free carrier concentration, resistivity 10 to -3. N type, nobody wants to buy them, so we don't grow them. And semi-insulating with manganese. So this is, they are today, we produce them, we produce such substrates, and we sell them. There are our competitors, so mainly Japan and China. Nobody in Europe. We are unique. I don't know if it's good or not good. I think very good. So I think I got 5 minutes or 4 minutes, because I would like to finish this talk with example of devices based on gallium nitride substrates, monothermal substrates. You know Schottky diode very well, you are a physicist. So this is in Schottky diode, substrate, drift layer, Schottky contact, metal contact, low terminal voltage, it's clear, high reverse leakage current, it's also clear. Well, we can do it. PN diode, same, but low reverse leakage current due to this P-type, high turn-on voltage also due to this P-type. But if we combine this Schottky with PN diodes, then we can obtain junction barrier Schottky diode with low turn-on voltage and low reverse leakage current. Okay? But we need here substrate, drift layer, selective P-type areas, and Schottky contact. How to do it? So in normal way, we can grow drift layer on our substrate, then create masking, then etching, then we can grow by MOVP or MBEP type. We can remove mask and we got it. The better way is implantation. So I think that implantation is the future for nitrides, okay? Implantation is used for silicon carbide. It must be used for nitrides too. But much easier. The problem is how to remove implantation damage and how to activate implanted dopants. And we got this high nitrogen pressure solution technology. So we can anneal GaN. We don't want to grow crystals now, but we can use the same equipment for annealing gallium nitride at high temperature under high pressure. Then we can remove implantation damage and we can activate implanted dopant. It works. So North Carolina State University, they cooperate with us and they prepared such structure for Schottky diode and junction barrier Schottky diode. This is a monogan. This is MOVPE, 5 micron thick layer. This is implanted areas of P-type activated by high pressure. And then they prepare contact. And they received very low RON on resistance, 0.6 milliohm centimeter square, and very high breakdown voltage for such thickness of the material, 5 microns, so almost 1000 volts. And ideality factor was close to 1, like should be. And on the Baliga figure of merit, have you heard about Baliga figure of merit? No? Okay. So this is the, for silicon is 1. This is on resistance, and this is breakdown voltage. Then you can see that for silicon carbide is much, much higher, this relation, and for gallium nitride is higher than for silicon carbide. So we can prepare high-power devices based on silicon carbide and better devices based on gallium nitride. What is important, that breakdown voltage depends on donor concentration in our material and thickness. If we can grow epi layers 100 micron thick, we can obtain even 10,000 volts breakdown voltage. So starting from MOVP 5 microns, we are here today. But yesterday, oops, it's not this in computers new version because I changed yesterday. Yesterday I received the new data from North Carolina. Then we grew 12 microns thick layer, so thicker layer. And we moved here, so we are now here, close to silicon. We are 1.2 RON with almost 2000 breakdown voltage. So this is the future for gallium nitride, to do MOSFET transistors and Schottky diodes, junction barriers, Schottky diodes for switches. This is very important. Gallium nitride can be better than silicon carbide, which is commercially available today. Believe me. So not only LEDs. Okay. And laser diodes. Also transistors. Hemp transistors also, not only on silicon carbide, but also our semi-insulating material. You know, no heat transfer, better heat transfer. There's the same material, gallium nitride. So at the end, summarizing, I would like to say, this is the slide from the Müller and Friedrich Encyclopedia of Condensed Matter Physics. So the bulk growth, melt growth. We didn't talk about melt growth, Czochralski and Kiropoulos and other method. This is the solution growth. We talked a little bit about solution growth among thermal flux, high pressure, and vapor growth. So mainly chemical vapor transport in case of gallium nitride, HVPE. Remember then silicon carbide, aluminum nitride, they are grown by physical vapor transport. And the last sentence from William Shockley, the material problem will have to be extensively worked on. One should not give up too soon. So please remember about it and work on in your domains and grow crystals and grow epi layers. Thank you.
Are there any questions? There were already 5, but still
So you showed, I don't know how far before, but there were a slide where there were temperature of the seeds and temperature of the substrates. And at the beginning, the seeds were stayed cool, and the material was hotter. And then you said that crucial is switching these temperatures to the growth phase. So I was wondering why in this first, when the temperatures were switched, the seeds were not dissolving in the...
So you are talking about ammonothermal growth, yes? And switching of the... Okay. And I find it. I think I find it. Oops, too many slides. Yeah. We are close. Here. Yeah. So, because this is backcatching. So we have to, at the beginning, we have to dissolve seeds in the solution. I call it for coupling with the solution. Without backcatching process, the backcatching, backmelting, wetting, without it, the growth will be polycrystalline. It's like that.
Thank you very much for the nice presentation. I have a quick question, and I hope I didn't miss it because I had to step out, but did you also talk about gallium nitride on insulator? Is this relevant? Because silicon on insulator, for example, is a very, very important topic and everywhere used, right?
So you are talking about Soitec technology, yes? And
actually, it's IBM invented it, but Soitec sells it.
Okay. You are from IBM, yes. Okay.
Oh, good.
No.
I just wonder because there are also often in the industry you want to also grow new materials on silicon because silicon is used for other areas and you need to bring new materials and stuff. So I wonder if there's something also which is important to you.
Yeah. So I was talking about semi-insulating crystals, but this technology for GaN exists for example, this is the smart cut. When we can remove this very thin layer and move to the silicon, for example, and I tried to do it with Soitec, and they told me many years ago, 10 years ago, and Leti, and the crystals were too small. Now we got 2-inch. They need 4-inch. I think then we can come back to them, and I still have the contact with Soitec and Leti, and maybe you're right, it will be possible, but they need bigger material. This is our problem. Today, nobody needs 2-inch. 2-inch is too small. 20 years ago, 30 years ago, when we started to work on gallium nitride, everybody dreamed about 2-inch. We got 2-inch, everybody thinks about 4-inch or 6-inch or 8-inch.
Further questions? So if not, then I think we can thank Professor Boczkowski again.
Thank you very much.
Unfortunately, to the tight schedule as the director of the institution and many other duties, he cannot stay with us for longer, so he'll leave tomorrow morning. But today he'll be with us at the barbecue.
Yes.
So please ask Michał questions and please interact. And
if you would like to visit Unipress, you are invited. So don't worry. Call us and visit Unipress. No problem. There are 5 localizations. There are many subjects. Hydrogen storages, not only gallium nitride, hydroxyapatite for bones, many subjects.
And there are other representatives in the audience, but also during the conference there will be many more. So yeah, you're welcome to interact and get involved in collaborations and visits. And so now we have a break. Let's make 25 minutes, then we can start 15 minutes ahead of schedule. So let's start at 5:45. And then maybe we can go to the barbecue also with this 15 minutes in advance. Not sure if this is ready, but I will ask. And yeah, let's have a coffee break. And I think it's a bit chilly here. We will try to increase the temperature, but it wasn't so easy before, as far as I understood. So maybe I see that it won't be easy. So maybe better please bring a jacket or something. So I will start with an announcement. Those of you who take part in the Best Poster competition, please upload it today. That's a message from the organizers of the main conference. And now we switch the topic to computers. So we will see the transition from classical to quantum computers. And we have a very distinguished guest who will tell us about it, Heike Riel from Zurich, from IBM Zurich. So Heike did her studies in Erlangen and did her PhD in 2003 at IBM, but formally it was Bayreuth, if I understood correctly. And she got a lot of distinctions already during that time due to her works on organic semiconductors and their applications as displays. And then at IBM, she works mainly on growing nanowires, but she also coordinates part of the activity of IBM that relates to quantum computing and superconducting qubits. Heike, please.
Thank you very much for the very, very kind introduction. I really appreciate, and thank you for bringing me here. It's a wonderful area, and I'm really very glad to be with you today. And so for me now, actually organic LEDs, as you just mentioned, right? We always try to avoid crystallinity because the films had to be amorphous to be most effective. But then I switched to nanowires, and they should be crystalline, right? And so working on semiconductors with organic LEDs, amorphous, then switching to crystalline, to 3-5 materials, and now to some extent being back on silicon and silicon germanium. And so I'm here really for you today. So you can ask me questions also in between. I have a lot of material with me because talking about computers, future of computing, neuromorphic computing, quantum computing, there's a lot to talk about. But it's not so important to go through all the material, but better that you really, have understand and also can ask your questions. So I'm also working for a company. I work for IBM. Who knows IBM? I'm glad, because we are actually no longer really make client products or like commodity products, which are normal consumes, but we more make enterprise computers. So we actually work mostly with big enterprises and deliver them big servers, which then make your credit card work. So every time you probably use a credit card, it runs over our servers, and they have a reliability of 7 nines. Because if you cannot draw money because of us, we have a big problem. So that's why our servers need to be really very reliable. And our mission in research, and this is where we are. So I'm located in Zurich. It's called Rüschlikon. That's a small village close to Zurich, and we are there since 56. Sorry, quite some time. It was the first lab of IBM outside of the US, and it has been grown over time. So you see, this is all, now I hope it works, the thing here. Okay, we tested it, but now okay, yes, now it works. Yeah, I'm a bit fast. So this is our campus, and this is our clean room, which is very important because we do a lot of work in that here. And this is where actually our science and technology areas is. And here we have a lot of computer science, artificial intelligence department. And this is the most important place. Do you know what this is? Yes. That's the cafeteria, the most important place. And this in the corner here, this is actually our systems department or hybrid cloud. We do also quite some circuit design and stuff. So we have actually not only software and services, but also a lot of hardware and computation and circuit design, which we do, and we consume actually a lot of wafers, also very special wafers, because our role is to really do exploratory research, because we typically actually work with 2-inch, maximum 4-inch, 6-inch, or even pieces, because we want to do a fast learning. And we also mess around in our clean room. It's not like a silicon line where you're very restricted by what material you can bring in. So we are the ones who can mess around if we've figured out the concept, if we know how it works, and if we trust that this is something which really should be in a line, then we actually transition this to our 8-inch line or even to our 300 millimeter line, right, if it's on silicon. So any material which we do, for us it's important that we can bring it on silicon. And so when we worked on nanowires and we started to work with gold, to use gold particles to grow nanowires, which is a very, which is a very common method. We already knew that this is not going to work for us because we cannot allow gold whatsoever in any silicon line. So we had to figure out other things, how to grow materials. So anything we do is always kind of driven, can we use it later? Or is it just for a paper? So we work a lot in collaborations also because we are very exploratory. And the lab, as I mentioned, it's already quite has quite a legacy. And also one legacy is that we had very important colleagues for us. Some are important for superconducting. They invented the high temperature superconductivity and got the Nobel Prize for. And then another one is actually Gerd Binnig and Heini Rohrer. And they are also, who uses an AFM? Has everyone used an AFM before? Has someone used a scanning tunneling microscope before? So they invented this actually. So these two guys, Heini Rohrer and Gerd Binnig, they invented first the scanning tunneling microscope and thus were for the first time making single atoms visible. So before that, no one saw, kind of a single atom in a direct way. And then Gerd Binnig, actually he was a really very smart guy. He continued to drive and together with then Christoph Gerber and Calvin Quaid from Stanford, they invented the AFM. And the AFM, I think, is an almost even more important technique because you don't need a current flow between your tip and your surface. So you can do an AFM, which is based on measuring the force of the tip to the substrate with also insulating substrates. And this has been used and further developed in many different versions, in liquid, with magnetic tips, with heatable tips, etc., etc. So it's a very, it's a method which is used really very broadly. But I don't want to talk about these methods, but this shows a bit also the spirit in our lab. It's, I would say it's between an industrial research lab and a university campus. And so what is our mission? Our mission is really to think about what is next in computing, always thinking ahead, what are the next things which we need in order to increase the computational power, in order to make computing more efficient. Energy consumption of computing is a big problem. And so this is what we are thinking about. And today what we see, and I just want to give it to you directly at the beginning, is that there are 3 types of different computing, and they will all coexist. And it's the bits, the classical computing, which we all know, where we compute with ones and zeros. And then there's the neurons, which is under the umbrella of neuromorphic computing, or also hardware for artificial intelligence. And then the third one is actually quantum bits. And I would like to touch a bit all of them and mostly speak about quantum bits. But I wanted to give you this full picture because I think we often dismiss what is possible or what is done in the conventional semiconductor industry in order to make all these devices which we use today possible. And so when we look at bits, then it started many years back with the first computers, and in 1946, the ENIAC, I'm sure you all have seen this picture. This is not using yet solid-state transistors, but using vacuum tubes. And these 2 people in this room, do you know what they do? Do you know why they need to be there? Yes, they needed to change the tubes because they were very unreliable. So lucky you that you don't need to change your transistors. So today things have evolved a lot, and there is a high performance computing is also driving a lot the further progression because we want to actually replace experiments by simulation. That's much faster and cheaper in the end, and you can do more variations than you would be able to do ever in your experiment. So high performance computing is very important. And so the biggest or the highest performing computer is today actually I think it changed just a month ago. It's no longer, no, it's Frontier, but it's since it broke the exaflop barrier, and it's now I think about 2 exaflops. So from 1 exaflop in 2022 to 2 exaflops this year in May 2023. And important is a number which is in brackets here, which is the how many flops you can make per watt. And if you look at this line, then this has also evolved quite a bit. And today these have 52 gigaflops per watt. On the other hand, we have all these gadgets which we carry around, where we can use our watches for calling other people. We have electric cars, which are computers on 4 wheels. We need more and more compute power in cars in order to make them really autonomously driving. And so there's a lot of compute power needed, and it's more powerful than ever, but it only works because we have these powerful computers. And so therefore, this is more and more important. Actually, the transistor last year in December had its 75th anniversary. And I think that's also quite impressive how transistors evolved since then. And I want to show this room again because actually, so not only because IBM Research was born in 1946 in New York, but also because today's labs where we compute look actually a bit similar. So what you see here is one of our quantum computing labs, where we have the quantum computers, the fridges here, and there's of course lots of electronics, and then all the cooling machines which are needed in order to produce low temperature in these fridges. So it looks a bit the same, but you will see later that we already have evolved that. So quantum computing has come into the game, and quantum computing is really a completely new computing paradigm compared to the classical computer. And it's the first time in history that there is kind of a branching of computation, and not only an evolvement of computation of classical computing with bits, but where we really use the quantum physics for computation, which is completely different. So now let's look at the transistor. Does everyone know how a transistor works? Yes, very good. So you have the source, you have the drain, you have here the channel, and you have your gate. And with the gate and the insulator here, you can create an electric field. And with this electric field, you can make this region then conducting or non-conducting, which means there is a current flow or non-current flow. So you have created a switch. And this, I'm sure you also have seen, this is the famous Gordon Moore chart, where he saw these 4 points, and he just put them down in a plot. And then, as typically as physicists we do, we draw a line through. And the amazing thing is that this line still holds till today. And it's amazing because it's actually not a physics law, it's an economic law. And every time it kind of was to saturate, and there were more investment done, and you keep going in. But you will see that by just increasing the density of the transistors, it's getting very, very difficult, because the transistors, meanwhile, they don't look like this. They look completely different. So in former times, we had like 50 transistors here. There were several hundred micrometers in size. And today we have more than 50 billion of transistors on a microcircuit. And they're all similar. They're all the same, actually. And the gate length, which is a very important length, is only 10 to 12 nanometer. And the contacted gate pitch is about smaller than 50 nanometer. And this needed a lot of innovation in lithography. And you can ask me a question about it later, but it's amazing what is possible there today. So the semiconductor scaling was over many times the key to enable faster computing with sufficient energy consumption. And this is how it evolved a bit. I mean, I started here actually only in 1999 with 180 nanometer gate lengths. then 130 nanometer, 90, etc., etc. And today we're actually in the product. So in the mobile phones, the product which you find has a gate length of only 5 nanometer. And we are working in development on 3 nanometer and 2 nanometer. And so we are not only approaching atomistic and quantum mechanical boundaries, we are already there. And for many years, smaller meant faster and cheaper. But this is actually since 2006 no longer true. Because you may not even remember that in former times we used the frequency as a measure for the performance of a computer. Everyone wanted a faster processor. And then we reached about 2 gigahertz. And why does it no longer work? Why do we not use the frequency anymore? Do you know? One knows? Yes, because the energy consumption is proportional to the frequency. So when you increase your frequency, you generate more heat and you cannot cool the thing and it melts. So the silicon you can bring to melt when you increase the frequency. So therefore we actually said, oh, if we can't increase the frequencies, then we use other multi-cores. So the multi-core was created. And of course, making smaller was always important, because making smaller means you get more transistors for the same money. And this is also why we want 300 millimeter, because then in one run we can get more transistors and thus can make the performance cheaper, and we can get all these gadgets which you can use and buy at a decent price. And so there were many inventions which were actually needed in order to decrease the size of the transistors. Like the high-K metal gate was a very important one, which was changing the silicon dioxide to aluminum oxide and hafnium oxide. Then the FinFET, and the FinFET I will show in a minute, because it shows that transistors completely look different to this planar architecture which I showed you before. And so I think this is also an interesting chart which says that there is a lots of research and innovation needed. So you won't, you will have a job. And the semiconductor industry is anyway right now increasing a lot. And what you see here is actually the gate lengths. So the generations or the technical nodes from 180 to 32. And you see the blue bar is a performance increase just by making the transistor smaller. Then you get higher performance. But when the law no longer holds, then you see you need new innovations, which means new materials, new architectures, new device structures, new processes to come in order to make your transistor higher performing. Because if you just make it smaller, it actually degrades in performance. So you need a lot of innovation to keep this law and this thing driving. So one of the important paths was to go away from this planar architecture. And why? Because if you make the transistor length, the gate length smaller in a planar architecture, then you also have to make the oxide thinner, that your electric field can control your charge carriers. But at a certain point, this is no longer possible, and you cannot control your charge carriers. If you can't control your charge carriers, what has happened? You cannot switch off your transistor. If you can't switch off your transistor, you don't really have a switch, and you have at an off electronic circuit, you have current running, which consumes power, and that's a no-go. And so therefore, we have moved to this other architecture here, which we call FinFET, which means now the silicon channel is actually this small fin with a high aspect ratio, and we have a gate which is on 3 sides of this fin. So we have now a much better electrical field where we control the charge carriers in this fin. That's the idea. And this has been implemented. It was very, very difficult to do this on 300 millimeter in this precision you needed, but it was possible to do it. And this is how these devices have looked like. And this is used for the 10 and 7 and also 5 nanometer node. So the transistor channel is now no longer planar, but it has become 3D. It required a lot of etching and also a lot of process know-how in order to make your gate homogeneously around this fin. And if you look at a cross section, then you see here actually the contacting of the source and the drain. And you see here some of the numbers. So the fin width is only 7 nanometer. The height is 46 nanometer. The pitch 34 nanometer. And the gate pitch is 54 nanometer. So it's really impressive what has been done. And what you see here is actually also a cross section to use such a processor. What you don't see is actually that the transistors are at the very bottom. You can't resolve them anymore. What you see above are all the electrical lines which are needed to connect the transistors. So now you can imagine what is a problem today is these lines become so small that the resistance increases so much that you actually have a lot of power consumption, ohmic loss. So capacitances, ohmic loss, parasitic resistances, parasitic capacitances are a big problem, and there's a lot of work to be done. And you may know that when the semiconductor industry started, we had aluminium used as these lines, but aluminium was too resistive, so one moved to copper, because copper has a lower resistivity. So now the lines get so small that actually aluminium is better than copper. So of course we don't want to go back to aluminium. So we look for a better material with a lower resistivity than copper at these dimensions which are needed. So you see there's a lot of challenges which we are working on to generate every time the next generation of technology. So what we have done over the last 10 years or so, we have actually worked on these nano sheets. And these nano sheets, they look a bit like fins, but they are laid over. And the advantage here is that now here you see this is a silicon now. There are 3 on top of each other, 3 silicon layers, crystalline material. And the gate oxide and the gate metal is wrapped around. So this is kind of the ultimate electrical or electrical field optimization of a device, that you get the best control over your charge carriers in your channel. And why do we need 3 layers on top of each other? Because otherwise it's so small we couldn't get enough current which you need for a transistor and building a decent circuit. So this is what has been done. And these devices are actually shown here at the bottom. This was the first generation in 2017, which we published, a gate all around stacked silicon nanosheet transistor to enable 5 nanometer chips. And as I mentioned, it has superior electrostatics as the metal goes around in the oxide. So the gate electrode is really wrapped around this nanosheet. And it has a much higher performance compared to these scaled FinFETs. And this is kind of the 3D sketch. You have your source. You have here the stacked silicon channel. And here's your drain. And these green things are insulators. And then on top here, there would be then the gate. So this is how it looked in the next generation of optimization. You see it's much better controlled, the edges, etc. And you see here the height of such a layer is about 5 nanometer. The width is about 12 nanometer. And we get 45% higher performance or 75% lower power consumption than today's 7 nanometer technology. And if you look at such a cross section, I really love this picture. This is a TM picture of a transistor where you see the source. And now I think, I'm not sure. Yeah, here the drain. This is a 5 nanometer high sheet. So it runs from the source to the drain. There are the inner spacers. You see they're really very thin, but they need to be insulating. And here you see the pitch. And this is done on 300 millimeter with this precision. This is if you zoom in into a nanosheet. It's not only silicon. There is a silicon core. Then there is a silicon germanium layer, which is needed to strain silicon germanium layer. And this is needed because with a strain, you actually can change your electronic structure, and thus you can increase your mobility. And this 1 nanometer silicon on top is a cap for the high K dielectric then to be deposited. So you create a compressively strained silicon germanium channel. And with this, you can actually uplift up to 100% the whole mobility in your devices. And you can also reduce reduce the channel resistance by 30%. So you see that there is a really high precision of control needed of the materials, the interfaces, the strain, and all this at the nanoscale. I think there was a question.
Yeah, so I'm very interested. How do you even obtain such slabs with
How that you can
silicon?
create the structure?
This
layered structure?
Yes. Could you
So it's a very
elaborate more?
sophisticated process. So what you actually start out with epitaxial layers of silicon, germanium, and germanium, and you use the germanium as a sacrificial layer. So you, it's an epitaxial step. You grow by MOCVD, and then at a certain point, when you have connected your sheets here to a layer, you etch out this inner material, and then you use ALD processes to deposit your gate dielectric and your gate metal. And then you etch actually away the base. You have your spacers created before, and then this is not implanted anymore. It's actually highly doped and regrown because implantation would no longer work. So at a certain point, in principle, you etch everything away and you rebuild it.
Okay.
Right? So this is actually no longer an implantation process to generate your source and drain with highly doped material, but you really etch away the material and then you regrow. And you regrow with highly doped material, and this is how you get the lowest source drain resistance and good contact material. So I think this is very impressive, what has been developed there, and all this on 300 millimeter. And actually, what the next step is, we think now about vertical transistors. And in a vertical transistor, which actually we built in our lab already more than 10 years ago. Here you have then a vertical transistor where you have the source at the bottom, the drain at the top, and then the current goes from the bottom to the top. And this has the advantage, then you can actually relax on the gate length, because you cannot make the gate length smaller. And here you can relax on the gate length without, without a disadvantage of the density. And so you can make it very dense with a higher gate length. And the other thing what is currently discussed and people working on is not only having one transistor layer, but having a second transistor layer on top in order to increase the density of transistors on the silicon substrate, because you kind of cannot make it smaller as what I've shown you. And so with these vertical transistors, there is the potential that we get out 2 times better performance or 85% less power consumption, which is also very important for mobile devices. It delivers more circuits per chip and also a wider operating voltage range, because we can go, as I mentioned, to a higher source drain lengths again. And I mentioned before that I started to work on nanowires in 2005. And in 2006, we had the first vertical silicon transistor. It looked really ugly, but it worked, kind of. But this was also done with this gold layer on top, right? And the test here, and this is the gate, you see it's not completely not conformal. It took us then about 4 or 5 years to create structures like this already, but not on, of course, 300 millimeter. And we then actually switched first lateral, and now, however, everyone is going back again vertical. But the idea here is we demonstrated all the concepts, so we understood what we can achieve, and then it was transitioned to 300 millimeter and integrated for really a product. So this is where we are. This is kind of where where we are going. But this is not all. There's a lot of other innovation and performance increase which we currently work on other layers. And one layer is all the interconnection. As I mentioned, we have to scale interconnections. And so so far everything has been done on the top. but now people start also to deliver power from the bottom. So kind of to make a lot of holes into the wafer, into the substrate, and deliver also current and voltage and power from the bottom. And on the other hand, there's also a lot of performance increase done by heterogeneously integrating different chips on a substrate to make the connections between them very small. And also here in this packaging technology, there is a lot of innovation currently in order to actually increase the performance of chips, of microprocessors further, in order to deliver the performance increase which we all need. So, and just to give you a few numbers of those high performance computers, this is one we built about 5 years ago or so, or 6 years even ago, which was called Summit. And it was the first to reach 200 quadrillion calculations, to 200 petaflops. And it had more than 9,000 Power 9 CPUs and more than 27,000 NVIDIA Voltage TPUs, 250 petabyte of storage. And what I always also like to show and to talk about is the power, the energy consumption which is needed. It consumes 15 megawatt. So 15 megawatt is quite a bit, but if you go back to another computer, an older one, which was the first to reach 20 petaflops, which was called Sequoia, it had 8 megawatt. So if you would have used the same technology, scale it up by 10 times, then you would be at 80 megawatt. So by technology improvements, we could already go to keep it at 50 megawatt. And so there's a lot of things which are going on here. And what is important that these nodes, the data is becoming more and more important because we all use AI. We all want to use AI. There's a lot of data we want to work with, unstructured data. And AI workloads need a lot of memory, very close to the logic. And so this is the next part actually I want to switch to, is that with this amazing number of growth of this exponential growth of unstructured data, we need to actually build specialized computers which can work with artificial intelligence. And so there is the question, why is AI actually already working? Because AI is not something new. Artificial intelligence has been invented in the 50s. So in the 70s, there were important also breakthroughs in learning, in algorithm development. And however, it didn't work. And you know why? Because there was just not enough compute power. So the compute power was not enough to calculate the neural networks you need in order to get the output you want. And only when these three trends came together, that there were better machine learning algorithms like deep learning, when you had massive data sets for training, which are labeled, and you had enough performance and also the cost of computing was low enough, then artificial intelligence was possible. So a big driver of the future also for AI will be to make computation cheaper and energy efficient. Because today, ChatGPT, has anyone looked at how much energy it needs to train the model? 1.2 gigawatt hours.
So I heard that in terms of money, it costs about a chocolate bar worth of money to ask a simple question to ChatGPT.
Yes, I mean, when we also use our mobile phones or stream movies, we always have to consider that it's always energy, because you always get data, right? You always get data down. And if you ask also in the internet, also if you ask the search machines any questions, that's always connected with some energy consumption. And the same is true for ChatGPT. I don't know how much it takes for asking a question, but for training the model, right, it took about 1.2 to 1.4 gigawatt hours. And it also takes a lot of time to train these models. So it may take like 2-3 months. And so there is a lot of desire to actually have faster and more energy efficient computing.
I have a question to the previous topic. So, as you have said, transistors are coming smaller and smaller, and I have a question: if tunneling is becoming an actual problem, in that case?
Oh, what is the problem?
Tunneling.
Tunneling, yes, definitely. Tunneling was already a problem many years back. And so because when there is a certain law of how you make a transistor smaller, and when you make it the gate length smaller, you need to make the gate oxide smaller to keep the electric field the same. And at a certain point, silicon dioxide became so thin that it was dominated by tunneling and it couldn't be used anymore. It was in the range of 1.8 nanometer. And then we had to replace the silicon dioxide by a material with a higher dielectric constant, because then you get the same capacitance by having a higher thickness. And this was a very difficult problem, and it was solved by a lot of tricks. But today we are using actually hafnium dioxide and aluminum oxide for making these capacitors, because then we can again have the thickness thicker and we avoid the tunneling. So definitely all this, and now you have seen the nano sheets, they are 5 nanometer. You cannot make it much smaller, because then you get in quantization. And then you also in silicon have quantization effects, which you do not want to have in your transistor. So all these problems actually lead to the fact that we may not be able to really make it smaller, but that we have to go in the third dimension to make another layer of silicon on top of each other in order to increase the density of transistors on the same area. So now we need to go to neurons, because we're looking actually for other devices, for other circuits where we can make these AI workloads be more efficient. And now you immediately realize that this is Mona Lisa, right? Everyone, you immediately saw, even though there are pixels missing, a computer would be not as fast. A classical computer, because he has to look at every pixel, he has to compare everything, but your brain is thinking completely different. And your brain actually is, however, not so good in making this calculation. At least mine. So, but computers are pretty good in doing that. And so our brain, however, has a significant advantage. It only needs 20 watt. So let's understand our brain. This was our hope. But then I talked actually to a colleague who's a neuroscientist who is working since more than 40 years on understanding the brain. And when I asked him, how did the brain work? He said to me, I don't know. I said, you're working on 40 years of this, so why don't you know? So it's not fully clear yet how the brain works. So it's not really useful for us to build a brain, because we don't know really how it works. So I needed to have a more practical approach to the problem. So what we did is we looked at the neural networks, and here is a classical neural networks. As I mentioned, it was invented in the 50s. The birth of the neural networks. Today, of course, you have deep learning, you have more complex neural networks. They have a really big depth. They have so many parameters. And the idea is you have an input layer, you have an output layer, you have hidden layers in between. And these lines here are actually the weights, how the neurons, which are the blue dots here, are connected with each other. And you train these networks, you thus train the weights. This means some weights increase, some weights decrease, and thus you train a network. And then you can bring in a picture and you get out the output, whether it's a cat or a dog. So now let's understand what is happening in these neural networks today. And in this picture, you actually see here the petaflops per day, which are needed for training on a logarithmic scale for the different neural networks which have been invented since about 10 years. So the early ones were low in energy, but you see that there's an exponential increase in the consumption of the power they need to get trained. And so it's actually the energy consumption doubles every 3.5 months, which is really tremendous. And this is this challenge we have, because we want to build hardware, which is actually, kind of solving that problem. And so we work on special hardware in order to accelerate these processes, in order to achieve the scaling and in order to make AI also more useful in the future. And we analyze these networks or these operations which need to be done. And this is actually shown here. You have different networks like the RNNs, DNNs, CNNs for vision, for language, for speech. And you see that this red bar is really the longest bar for all of them. And this is actually a general matrix multiplication and addition. So all these networks, the biggest operation they need to do is multiplying matrices and adding numbers up. And so what we are looking for is now computation and new computers to do this much more efficient than our general processors. And of course, the GPUs were the first one which were better in doing this. But we want to become much better than GPUs. So the matrix multiplication constitutes about 70 to 90% of the total learning. And so there are new approaches to actually trade also the precision in computation for the computation efficiency. So we can do algorithmic improvements and cannot work with 64 bits, but we reduce the precision, go down to 16, 8-bit, 4-bit, and thus actually get higher speed and higher energy efficiency. And with this, we have built new processors according to these guidelines here, that when you reduce the precision, then you can actually improve the energy efficiency quadratically. And this is what we are using in these. I don't know, I want to speed up a bit here. We have investigated this and developed new digital, these are digital cores, but they have a different precision. And you see here for training, going from 32-bit to 16-bit to 8-bit and to 4-bit. That's actually what we demonstrated about 3 years ago, that we can train neural networks with 4-bit. And this is done then at much lower energy. And the same is actually true here for the inference, where you can even go down to 2-bit. So we have built those processors, and we have integrated them already in products. And this is actually our new C16 chip. And there is an AI core, which is here at the corner. And this AI core is currently used that we can detect much faster the fraud on your credit cards. In former times, this took a while until it could be done, but now with this AI engine on the chip, we can actually detect in a few milliseconds whether fraud has been done with your credit card. So this is practical application, but we want to become better. And so what we do in research is actually look at another fundamental problem, which is that in the so-called von Neumann architectures, we have a logic chip and we have the memory, and we have a bus in between. And when we do calculations, then we always have to provide data and shuffle data around between the memory and the GPU. And for each of those matrix multiplications, we have to do this. And this costs actually the most energy in those processors. And what we want to do is actually go to a so-called in-memory chip, where we have the memory and the analog and an analog component together, and thus be able actually to avoid that we need to shift this energy around, and do not lose time and do not lose energy by shifting the information around. And so I want to explain you on the next chart how this works. So I think I can skip over this. This shows again that this multiplication and addition, but I don't want to go into detail actually, this I shift. But I want to explain you how an analog would work, how an analog circuit could actually do a multiplication and an addition. And that's actually very easy, because here you have a crossbar architecture where you have lateral lines, horizontal lines, you have vertical lines, and these orange devices are so-called non-volatile elements, which have a certain conductivity or resistivity. And you can control this resistivity. And so what you do is, you can now look at this multiplication or matrix multiplication, where you have here your voltages on each of the lines. You have then your weight stored as a conductance at each point, and you just have to use Ohm's law and Kirchhoff's law, and you add up your current, and you have done your matrix multiplication. So with this technique, you can in parallel at the same time do your matrix multiplication. What is important is that actually you have here a tunable resistance, which is non-volatile. And this is then your synaptic weight in your neural network. And this allows you then to be used for forward and backward propagation and weight update, etc. But there are a few things which need to be taken into account, that this resistance or the characteristics of this device needs to be like symmetric. Because when you do training of such a chip, then you want to do an increase of your weight or a decrease of your weight in a similar manner. And so therefore we are currently looking in our research into devices and physical mechanisms which can deliver the symmetry of non-volatility. And one example is here, a non-volatile memory is a so-called phase change memory you may have heard of, where you have a crystalline phase and an amorphous phase, and you can then change the ratio of the two phases in your volume, and this then changes your resistivity of your device. And this you can actually is non-volatile. So you can put it in a certain state, in a certain ratio, you can keep it there. And this is actually working similar like a CD worked in history, right? And so you can do this with a so-called phase change memory. But the problem here is that this is not really a symmetric characteristic. It's like a non-ideal characteristic, but you can use it for training somewhere else, adding. So you train in principle with a different digital computer, and then you put the weight on your phase change memory, and then you can run inference jobs. But if you want to train also, then you need other materials. And what we're investigating right now is actually resistive RAM. We have done quite a progress. So we have actually already almost a symmetric characteristic with resistive RAM, or also electrochemical cells actually give a nice symmetric curve. Also magnetic domain wall motion, or also and also ferroelectrica are considered for those type of devices. And currently the research is done in order to get these devices symmetric, and also scaling down to the sizes which are needed, etc., etc. So now I think this was the part which I would like to summarize, that there is a lot of things going on the AI hardware part, where we have now the bits I've shown you, how they continue, and this is how the neurons continue, where we have traditional CMOS, which is a so-called von Neumann, where we worked with GPUs, we do this approximate computing, and then there is this other path where we work in analog in-memory computing, where we have this analog circuits where we can then do really parallel calculation of such a matrix. And then the next step is, of course, understanding the brain and mimicking the brain. But this is something where we need more research and more work to be done. And then I would actually like to continue with the qubits. And so we can make a quick break for questions. And I will switch actually my presentation here. And I listen to your question. So feel free to ask a question if you have one.
I have a question. I wanted to know, if it's not a secret, how much more expensive is this stacking architecture in comparison to FinFET?
So I cannot answer you that question.
Okay, thank you.
You know, the complexity of developing these technologies is increasing very heavily, and it needs a lot of investment. So also the machine which you need for doing the lithography today is a so-called extreme UV machine, XUV, and just this machine costs 150 million. Just one single machine of those things. It weighs about 12 tons, and it's a hell lot complexity. It uses 13.5 nanometer light. Does anyone know how this 13.5 nanometer light is generated?
Yeah, we discussed it last week.
Yes, exactly. It's a thin droplet which is hit by a laser, and then you excite it, you create an excited state, and you get the 13.5 nanometer out. Can you imagine how difficult this is? Because you need also power. You need power, light power coming out, that you can run 250 wafers per hour through this machine. So and so I have no idea how expensive it is, but you see it in the end, because there are only a few companies in the world who produce these things, right? We do a lot of research and development, and we work with companies who produce it. So there is Samsung, there is Taiwan Semiconductor Manufacturing Company, TSMC, and there's Intel. So you see, it's very, very expensive to build those tools. And if you need also a lot of products to run through, that it's worthwhile doing it. So it's ASML who builds the machine, Trumpf builds the lasers, and Zeiss builds the optic. So this is one of the European, great companies who are there in the semiconductor area, where the others rely on, right? Because without this machine, there is no manufacturing of these chips.
You showed that this silicon germanium alloy on these silicon fins allows to increase the mobility of the holes, as you showed, yes?
Yeah.
And there is some way to increase also maybe mobility for electrons, because I understand this is for P-type.
Yes, typically it's a different type of strain.
Yeah.
So one is compressive, the other one is tensile.
Yeah, but is there some way to increase also, or some method used to increase the mobility for the N-type?
Yeah, that's also done. That's also done.
Similar way, yeah?
Yes.
Okay. Thank you.
Alexander?
So according to the same topic, because you mentioned that the strain is well controlled, however, there are two materials with different thermal coefficients. So when these processors are working, so I guess everything should be taken into account. So I wonder what is the difference when the processor is cold, when it starts, and after long running, if everything compensates or it degrades, for example, the performance of transistor.
So actually the temperature difference during fabrications are more important than the temperature difference during running.
Okay.
Because there you have process steps and you need to be very careful which process steps you do, then you have the strain at the end you need.
Okay, thank you.
Do you see any future for 3.5s to?
Actually, it's, I have worked a lot on 3.5s for actually building the next generation of transistors and kind of wouldn't say replace silicon, but add on silicon. And right now for CMOS, like 3.5 CMOS, we have done actually the leading edge devices on 3.5 CMOS in our lab in Zurich, also for RF devices. But I don't see that we get better than what you can do here.
So when you develop this chip, so this, for example, the chip that you showed in the few last slides, so the very big one with AI enhancement. So do you develop it and then you produce it and you sell this intellectual property to?
So we work for a long, we had our own fabs. In 2015, we actually sold our fabs because we had not enough chips to make in order to have useful, but we continue to do our research because we have the most complex chips in order to get this reliability, which I spoke before, and also the performance. So our processors are actually the largest which are built. And so we need to do a certain tricks on ourselves, which we need to develop. And then we actually transition to the manufacturers which we work with. And so some of the manufacturers also come to us because we have developed these sophisticated processes because they're interested in our IP, as you said. And there have been also recently a big deal, which you may have read in the news. You probably know that the semiconductor is, since Corona and the supply chain problems and also the political situation, that countries want to create more competences. Again, also, you have seen the CHIPS Act probably, the European CHIPS Act, the US CHIPS Act, and Japan, for example, just end of last year, they have created a semiconductor company, so-called Rapidus. It's owned by several companies in Japan, and they come to us because they want to learn from us and they want to learn, get help in how to build up such a company.
Okay, thank you.
So that's one business model of research.
So we can continue.
Yeah. So then I would actually continue. Time is running, right? And everyone is looking for the barbecue. So I'm in a very difficult situation.
Is there a need of break, or shall we continue? I think we can continue and go earlier for a barbecue. 5 minutes.
5 minute break. Okay, yeah. Very good. Then let's take a 5-minute break. And I hope you don't disappear. So you know that
Okay, please take your seats. We will continue. So this was a bit long, 5 minutes.
So thank you very much for staying. I want to now continue with quantum computing. That's another very, very interesting type of computing, which I mentioned already at the beginning, is completely different to what we are used in the digital work or analog work. And already I'm sure everyone has seen this picture, right? It's a picture which got kind of synonymous for quantum computing. But what you actually see is just a fridge. So what you mainly see is really the instrument for cooling down the processor and the microwave cables going down to bring the microwave signals to the processor. And so what you see here is the inner of such a fridge, where we have different cooling plates. Now I hope that the thing goes back here. Okay. I think I need to quickly, change that to the laser pointer. And so the chip is actually at the bottom here. And now we are back. Okay, now it's going. So here's the chip. And these are actually then microwave cables, and the chip is at around 10 millikelvin, and all the other stuff is needed to go down from room temperature to very low temperature and insulate the sensitive qubits from the noise. And now I want to dive a bit into quantum computing, qubits, and start with that. Of course, it's very different to classical physics, because in classical physics, where we use information carriers in our physical world, these states which are using the bits are reliably distinguishable. At every state in our computation with bits, we know whether they are a 1 or a 0. And we can observe them, we can measure them without disturbing them. And this makes it very easy because we can error correct them, we can do a lot of this. But this actually goes away when we go to quantum computing. And when we go to quantum physics, then as soon as we measure the state, we disturb the state. And this makes it very difficult to then also, for example, implement error correction. And also, we have the uncertainty principle. So when we attempt to observe a state, we disturb it, and we obtain only partial information about the state. And however, we can also use new things. We can entangle qubits. We can use interference. And with the entangled state, this causes them to behave in ways which is not possible in classical, and it can only be explained by supposing no longer explain that supposing that each particle has some state of it. Bloch sphere, which indicates a qubit, where we have then the states, the ground state 0, or the excited state 1, for example, which the superposition of alpha times 0 plus beta times 1 represents then every state in the Bloch sphere, and this is then represents our qubit. So it looks more complex, and it can do many more things, and we can entangle then 2 of those qubits, etc., etc. So in a classical, as I mentioned before, you have the n input in a computer. You do something within your computer. Again, you know at each state that you have like an n-bit intermediate state, 0, 1, 0, 0, for example, and you get an n-bit output state. However, in quantum computing, it's completely different. You again also use an n input, but then within your computation, you can use superposition, you can use entanglement, and you suddenly have 2 to the power of n complex numbers and a very big state which you can use for computation. But when you measure, then you also only get an n-bit output state. And so during the computation, quantum computers have access to these non-classical resources of superposition and entanglement and interference, which can speed up calculations. But it needs also specific algorithms, quantum algorithms, which make use of these physics. And now I would like to go on with by analogy. We know about the bit, and a bit in a computer, we have like different gates which we are using. So what I drew here is kind of an example of a classic logic circuit. You have a set of gate operations. And with this set of gate operations, you then have also the unit of computation. So with a set like an AND and a XOR, you can do in principle every computation by this universal gate set. And the same is actually true for the quantum bits or quantum circuits. You have again here the Bloch sphere of the qubit. And you also have a so-called quantum circuit, which is indicated here as one qubit and another qubit. And we draw them like this line. And on this line, then we can apply gate operations. This would be here a C0 gate, which entangles these two qubits. And this would be an Adamar gate, which creates a superposition. And so this is then, we call this a quantum circuit, which we call then the unit of computation. And in the, again, here you have the superposition. And as you know from quantum mechanics, these are complex numbers, alpha and beta. They have to be 1 because the probability that you measure the state of 0 or 1 is then 1. And then here you can create then also entangled qubit state as shown here. This is a bit the math behind. Now, what people have been doing in the 90s, after David DiVincenzo, a former colleague of mine, has told the physicists, the experimentalists, how to look for in order to build a qubit with the 5 DiVincenzo criteria, people went out and looked for physical implementations to build a qubit. And you can think of the atom as a quantum bit, because in an atom, you have an anharmonic energy spectrum as shown here. You have, this leads then to here these different energy states. You have the ground state, you have the first excited state, you have other excited states, but you also see that the energy you need from 0 to 1 is different than the one from 1 to 2. And this is actually very important because this is key that you can operate a qubit. So you need a anharmonic energy spectrum in order to be able to build such a qubit. And you want, of course, low loss, and you want to have your qubit isolated from the environment, because otherwise you also degrade your quantum information. So then we can also actually show such an artificial atom as like a oscillator with a capacitance as an inductance, which is often used when you then want to build these circuits and do also microwave, you build your microwave circuit, which you in the end have for superconducting qubits. And what we are using at IBM superconducting Josephson junction as qubits, where you have then, in this case, it's actually a harmonic oscillator, where you have an LC oscillator, and this is represented then in this harmonic energy diagram, where you have 0, 1, 2, 3, they're all equidistant, but this is for a qubit not really useful, as I mentioned before, because otherwise you would not be able to control between the 0 and 1 state. So you really need an anharmonic energy spectrum. And this is what you get when you actually use an anharmonic oscillator, in principle a non-linear inductor, and the Josephson junction actually is a non-linear inductor, and this is why it's a very interesting a component for building those quantum bits. And then you have this anharmonic energy spectrum. You get your 0 level and your 1 level, and the next level is actually at a different distance, and thus you can control these two levels. So you have then you actually use all these components. You go from the energy level to the anharmonic oscillator. It's shown in a physical circuit model. And then here, this is an example of how it's implemented. So what you see here are actually 4 qubits. No, sorry. I'm not sure what I'm not sure where the battery is now over, actually. Perhaps you can check. Okay, I'll use this one. Okay, so here what you see is actually this is a Jaszowiec junction, and these are then couplers between the Jaszowiec junction, and these are resonators to the outside world to connect. So you have the idealization, you have the circuit, and you have also the physical realization and implementation. So when we go to quantum hardware, then there are many different types and implementations which have meanwhile found and which are meanwhile investigated. So people use trapped ions, very similar to an atom. Also neutral atoms are used. There are photons used also for quantum computation, and superconducting qubits, as I mentioned, which are based on superconducting Jaszowiec junctions. Spins or quantum dots you can also use, so electrons or holes, the spin of them can be used. Also, other solid-state qubits are currently investigating, like Andreev qubits, or also so-called Majorana qubits, which still have to be demonstrated, but they would be topological and therefore quite interesting. And there are also solid-state defects like nitrogen vacancy centers in diamond, or phosphor in silicon-28, or also dimers in silicon carbide. These all can be used at these two-level systems which you can build a qubit from. And so we actually investigate at IBM superconducting circuits and also spins or so-called quantum dots. So now I would like to focus on superconducting qubits a bit and show you here one of the pictures of a smaller circuit which we have produced a while ago, where you see again here the superconducting qubit, this quarter here. And then you have here these microwave quantum bus resonators. They connect different qubits. You have microwave readout resonators. And these resonators, these are actually harmonic elements. And this is actually what you see here. Again, if you go to the superconducting qubit, it's a quantum information carrier, the Jaszowiec junction. It's a junction, a tunnel junction out of a superconductor, an insulator, and a superconductor, which acts as this nonlinear inductor, which I mentioned, which makes the energy spectrum anharmonic. And the distance between this ground state and the one state is about 5 gigahertz, or about 240 millikelvin. And this is a reason why we need to work at around 10 millikelvin, because you want to be, again, like a factor of 10 lower than your distance between the 0 and ground state. The junction itself is about 100 times 100 nanometer. And you have here the superconducting metal, then an insulator in between, and then you see here the cross in order to build the sandwich structure. And this is shunted by a capacitor. And what we today achieve is coherence times in the range of 100 microseconds up to milliseconds. I will talk about this later a bit. And also the gate operation time. This is the time it takes until you operate on your qubit, which means until you shift your arrow in your Bloch sphere around, or you entangle qubits. And so the 2 qubit gates are a bit longer, but in the range of 500 nanoseconds or a few hundred nanoseconds, and the single qubit gates are pretty fast. And this is also important when you look at all the other options. You want to have a fast option, because if you have an intrinsically slow qubit, then you have a hard time to end up with a fast computer. So then you have these superconducting microwave resonators, which I mentioned, and these are actually harmonic oscillators. They have a harmonic spectrum, and they are used to read out the qubits or to connect between 2 qubits. And they're also used as filtering out the noise, because you want to make sure that only the right pulses come in and no noise goes in. So the gate operations, or how to control these qubit states, is done by actually microwave pulses. So the single qubit gates, they are implemented by applying different microwave frequency pulses in the range of these 5 gigahertz that I mentioned. So you have here your wave function, and this wave function you then drive around with the pulse along the line, right? And what you can do is the amplitude and duration of the pulse controls the angle of rotation, and the phase of the pulse you apply controls the axis of rotation. And of course, you have to make this very, very accurate, because otherwise you create errors, and errors, as we learned, are hard to control. And therefore, there is a lot of optimization also done in order to create and to shape the right pulses that you get the right result. So then you have, these are the single qubit gates, but we also need 2 qubit gates in order to entangle 2 qubits. And this is done by qubit-qubit interactions, where you have here 1 qubit, you have another qubit here, and you can actually implement such a 2 qubit gate by driving the qubit 1 at the resonance frequency of the qubit 2, and thus you can achieve like a conditional rotation of qubit 2, and these gate times, as I mentioned, are in the range of 100 to 500 nanoseconds. And the other thing is, you also need, at a certain point, you want to read out your result. And the readout is done by coupling your qubit to a resonator. And when you have it coupled to a resonator, then the cavity frequency shifts slightly depending on the qubit state. And this you can then measure. So these are the kind of building blocks which you need in order to build such a system, or a qubit, or a processor. Because when you look at the system, which we do right now, then there are actually many more components that you need in order to make the computer work. So you have your fridge, you have your chip, which you cool down to around 10 millikelvin. Then you have here already like noise filters and a lot of stuff. And then you have a full rack of electronics which you need, like analog microwave components and signal digitization, or field programmable gate array based microwave pulse generators and control units, or who shape the pulses also. You also need stable microwave sources and a lot of electronics, which is actually at room temperature, which you then can control and do your entire calculation. Important is that this is stable, it's low noise, and of course, if you want to scale up the number of qubits, that you also have to be cheap at a certain point. And so there is more things you need to take into account, like thermalization and cryogenic stability, the coaxial cabling, and the I/O signal integrity. You have to also isolators for the microwave signals, amplifiers, like low noise amplifiers at cryogenic temperature, and of course then the quantum processor sitting here. So we are working also now in order to bring down electronics, to miniaturize the room temperature electronics into smaller pieces, which are cheaper, which are miniaturized, which are integrated, and also actually think about whether we can bring some electronic to around 4 Kelvin in order to get some benefit. And that's something which we have started to investigate a few years back. And we have built, meanwhile, also some electronics, and here you see the whole kind of system from an electronics perspective, like qubit state detectors, also like voltage control oscillators, which are based on AD converters, and also here like a directed digital synthesis radio for DA conversion. So we are testing and building and seeing how we can improve the electronics in order to get less noise, get more stable, and also get cheaper. So I've shown you this picture before, that we are now, we are of course continuing to work in the lab and improve, because there's lots of work to be done on quantum computation, right? It's a bit like in the 60s, 70s in semiconductor technology. So there's many, many more stuff to be done. But we have meanwhile actually built already computers which are no longer only in a lab, but actually in a quantum computing data center, or in a normal data center. And they look more styled, of course. What you see here is a fridge with the instrumentation behind, and behind this wall there is actually then also the vacuum pumps, the electronics, and all the other stuff which you need. And meanwhile, we have these type of computers since more than 7 years on the cloud for everyone to use for education, training, testing, and accelerating and advancing the research, algorithm development, etc., etc. So 25 systems, meanwhile, are online. We have built already many more of those systems, and there are already more than 460,000 users who use those systems online. Also, we work very closely together with also people who do, who want to use and build use cases for quantum computation to apply them also to real world problems. And also a lot of research papers have actually been published already by using these computers. So the research has been quite a lot accelerated by making these things also, available. So important for driving a technology is always that you know what you need to improve. And this is sometimes not so, easy, that you define the benchmark, that you define the true benchmark you need to improve. And so that's part of our research also to look at what do we need to improve, what is the right benchmark to also compare the different implementations of quantum bits with each other. And so scale is definitely important because you need to be able to build a processor with a high number of qubits. The quality is also very, very critical, that the quality of the qubits that you can really do quantum calculations is very high. And then in the end that you also get your result back in decent time. So the so-called circuit execution speed. And I want to talk a bit about scale, how we build those processes. I think it switched too fast, sorry. Sorry, something went wrong. Let's go back. Okay, so meanwhile, we have built actually a processor which has 433 qubits. We started in 2019 with 27 qubits, 65 qubits. Eagle then was called with 127 qubits, and last year in November we demonstrated one with 433 qubits, and right now we work in research actually to get one with 1,000 qubits or with more than 1,000 qubits done. And the packaging becomes also very important, and this should be seen on the next chart, because meanwhile, if you have 433 qubits, you can no longer connect all the qubits within one layer. And so this is a qubit layer. They're actually the resonator layer, and this is a layer where you can connect all the qubits with each other. And this then has to be done all together in a package, which you can then also cool down to 10 millikelvin, which is, we discussed the materials properties before. It's also very important to have the right materials, that you don't create a lot of strain there, or that the package doesn't hold. So the layout of such a processor looks like here. So on these are the connected qubits. So each kind of dot is a qubit. And you may wonder why they are connected in this architecture. This has to do with like a error correction code, which we want to pursue. So you have like 3 and 2 connected with each other. And this architecture is kind of a trade-off between avoiding noise and, how is it called? Crosstalk between different qubits, but also achieving a decent interconnectivity between qubits. And so this is a quick cross-section through such a package, where you then have your qubit wafer. You have here bump bonds. You have then a superconductor, then a wafer with interposers, where you have the through substrate vias. And then here you have all the multi-level wiring, also for the certain dielectric. Here you have also your microwave lines. And so this here is an example then of a cross-section in a real version. And so you need really to well isolate it from the interposer and the qubit metal levels. You want to control in the readout signals through all the strip lines as this multi-level wiring layer. and connect then everything through this through substrate vias to your qubit wafer in order to be able to connect all of them. So one other thing, if you build such a processor, you need to make sure that you have a high yield. Because if you can't achieve a high yield, you will never make enough yield to get a 1,000 qubit processor. And this was one of the early problems which we had, that the yield of achieving the right frequency was varying too much. So what you see here is actually a kind of a number of qubit plot and the frequency which you get out of the tunnel junction. So in the Jaszowiec junction has a certain frequency, and we all know a tunnel junction is very sensitive to the thickness of the insulator. But you also have a certain variability in your processing, and we needed to really be able to control that. But even if you control it well, you have a certain variability. And this is what we see here in this distribution, this pinkish distribution, that we have quite a variance of the different frequencies of the qubits which we built. And what we learned is that by laser annealing, we can actually tune the frequency of the Jaszowiec junction. And due to this law of the frequency of the Jaszowiec junction and the resistivity at room temperature, we were able to tune at room temperature the resistivity and get then at low temperature a certain frequency, which is actually our target frequency. And with this, we were able to then really learn that we can tune all these frequencies to the number which we want very precisely, and thus are able to actually achieve a very high yield in these processors, because you need to hit a certain frequency in order to make the thing work. And so with laser annealing, we could effectively, after the fabrication, trim the frequency and thus create a high yield, which is critical, as I mentioned, to the 1,000 qubit processor, and also keep or improve the 2 qubit gate fidelities by tuning the frequency to certain points. So now the next problem is when you scale up to high number of qubits, these wires, they are too big. So if you want to have 1,000 qubits in a processor and you want to have the 9,000 cables going down, actually we are using multiplexing already, but even then, you need to come up with something different. And what we came up with, it looks not as shiny anymore, but it's much more useful, because these are now actually so-called flex lines, where you have a multitude of lines in those flex lines, and you can thus make and build it very compact and scale up to high number of qubits. Then, as you can imagine, the next thing is the electronics, which I indicated already. When we started in 2016 with a 5 qubit processor, we had all these lab instruments, right, where you have like a number of money for one of those qubits, and this is not scalable. In a first generation electronics which we built, we then were able to use one rack for 20 qubits. We further improved in generation 2 and needed not even a full rack for 40 qubits. And last year we were able to demonstrate actually the 400 qubits with just a third of a rack. And this is really necessary for scaling up, because you need to get better stability, less noise, and you also get a higher number of qubits. And the next step is now, what I indicated before, is that we go to integrate this further on a CMOS controller, which is even smaller. And this we have demonstrated last year for the first time, that we built this chip. It's running well, and this is then put at 4 Kelvin, and it's the first kind of fully featured cryo-CMOS qubit controller, which has sequencing control and mixing, and can thus also create higher quality. So quality is one important part. And for quality, coherence times are also important. There are many different things, many parameters which are important for achieving high quality of computation, for quantum computation. And one part is the coherence times. And coherence times, you have like T1 and T2 times. And the T1 is the relaxation, or the time it takes from the qubit to decay from the 1 state to 0. And the T5 is the dephasing time of the randomization of the frequency. And this is when the time to lose the phase, right? And so these are important parameters. There are certain sequences of how these are measured. I don't want to go into detail, but the T2 times is shown here for how it was for many, many years, right? And you see here the coherence time, again, as a function of, on a logarithmic scale, as a function of the year the paper or the work was demonstrated. And you see 1999, it was like nanoseconds. You cannot really do a useful quantum computation in a nanosecond, but there has been a lot of improvement over the years, and it came really in a range where you can do computation with it. And you see a lot of the things which had to be improved. The type of the qubit, improvements in materials, in processing, in design of your microwave circuitry, of the microwave engineering was very critical. Also shielding, infrared shielding, thermalization, filtering of the outside world, the circuit design, building high Q cavities, also the packaging, any surface contamination. So you really need to avoid loss here. And so there has been a remarkable progress, but we also want to come up to about 5 to 10 milliseconds, because it's important to then do also quantum error correction. And what we achieved recently was that we were able to improve the coherence times from the range of 30 to 100, where people typically are, to more than a millisecond. And you see here that we work with test devices where we already reach above 1 millisecond. And these are the so-called processors. The Falcon has 27 qubits, and R5 means revision 5, or R8 revision 8 means you learn, you improve, and in your next version, you then implement the improvements, right? And this is then an R8 is kind of the revision 8, and this has certain improvements which we learned from here. And the other very important parameter is the so-called gate fidelity. And this is the so-called C0 error rate, where when you do a 2-qubit gate, you have a certain error because of, you need to shift, you need to bring, in your frequency, in your pulsing, etc. And this you again see here the error rate as a function of time, and low error means on this side. So we also improved here the error from 0.01 to now about 7 times 10 to the minus 3, but we need to improve also further here, and we want to achieve like 10 to the minus 4 and beyond soon. Speed. Speed is critical, and for speed, not only the qubit is important, but the entire interaction also with your classical world. Because in a quantum computation, you have a classical computer, you have a quantum computer, and they have to interact with each other. And how you build your entire architecture will also influence the speed of your computation in the end. And so we have defined a benchmark, which we call CLOPS, or circuit layer operations per second. And this takes into account the circuit execution time, the runtime, so the compilation of your program is also important, the data transfer, circuit delay, and many other things. And so what is important for this is that you have fast gate. I indicated it before. If you have a slow intrinsic gate, you will never reach a fast computation. That you have a high fidelity, fast readout, so you need also the electronic circuitry to be optimized, advanced electronics, and also the right compiler, and also the right architecture of how your classical and your quantum computer interact with each other. And over the years, we have also improved here the times by code pipelining. So these are a lot of software techniques, also controlling the systems, the quantum engine readout, and also the compilation. And meanwhile, we reach 15,700 CLOPS. I mean, that's a number, of course, we further need to increase in order to make the quantum computation fast. So quantum computing, we know from the silicon technology that a roadmap is always very helpful, because in a roadmap, the entire ecosystem knows when what is needed. So when does ASML needs to have like the machine ready? When does the silicon industry, when does the materials provider have the corresponding photoresist ready? And when can a consumer also get the right chip then ready, right? So roadmaps are always very important to also create an ecosystem, to create also a market. And we have started to build such a roadmap of what we want to deliver at which time. And this helps not only the external world to understand what we want to do, but also actually it helps to focus your own employees on the important problems to be solved. And so what you see here are the first things which we already delivered from 2019, 2020, 2021, and 2022. You have at the bottom the hardware, so the different processors is 27, 65, 127, 433 qubits. And then on top, we also need software, because otherwise only quantum physicists in the lab would be able to operate them. But that's not the goal. The goal is really to build in a software stack that everyone who uses Python can program a quantum computer. And this, of course, needs a lot of abstraction, and we are working on this, and we have actually divided this into 3 different types of developers or software engineers. The ones who understand the hardware also quite well, because they need to build quantum circuits. They need to build the so-called Qiskit runtime, dynamic circuits, etc. And then on top, there are developers who want to develop an algorithm, and they can use then these circuit primitives to implement the algorithm. And then on top there, the model developers, they just want to solve a problem, and they can use these implemented algorithms to solve their problem. So that's kind of the idea behind. And this year we have again a challenging year where we want to demonstrate, as I mentioned, the so-called Condor chip with more than 1,100 qubits. And we also started in parallel another path where we build modularity. And this is a bit like multi-core, which you all know. Because in the end, you have a bigger problem and you can divide it into smaller problems and you can run that parallel. Or you have one problem and you can run that problem parallel and you can average later. And we start this year by building a modular, like a multi-core processor, which consists of 133 qubits chips, which are classically connected with each other. And classically means that there is no quantum information exchange between them. But you can take the result from one, and within the coherence time, you can influence the next programming step of the other. And this has an advantage, which is in order to reduce your quantum circuit into smaller circuits, and thus have more you can do within the coherence time you have available. It's now a bit abstract, but it really helps to make more computations in the same time. And the next year, we want to extend this to a processor, which is so-called cross-bill, where we then connect these cores by so-called qubit gates. So which means that we now can operate these 2 chips or these and create a quantum bus between them. And by this, these 3 cores are connected with a quantum communication line, and thus they appear as a big chip to the outside world. And with this, now we want to create modularity that we can easier scale up by not building just bigger chips, but by using multiple cores and bringing them together with classical, but of course with quantum in the end. And this, we want to use these different modular approaches in order to build then a chip with more than 4,000 qubits in 2025. And you can imagine how it continues. Of course, there will be more in the future. And this plot was defined in end of last year. But just like 2 weeks ago, we announced that by 2033, we want to build a processor with 100,000 qubits. And so you can imagine there is quite a lot of work to be done till then. But you see there is also a scaling which is, quite interesting. And of course, on top, there's a lot of software which is developed to make it easy to use the quantum computers, create also error mitigation techniques, error correction techniques, and thus build really the computational platform up. So the question now may be, what do we do with such a quantum computer, different to classical computing? And I want to show you this chart here, where you see if you want to simulate classically, so with a classical computer, you want to simulate qubits. then you see how your classical resources scale with the number of qubits you want to simulate. And you see if you go up, you easily reach soon a line which you can no longer simulate. So you cannot simulate classically a qubit machine with more than 100 qubits because of the exponential increase of the information you have in qubits. And this is the significant potential, but also the challenge in order to control this. And this allows you then to solve problems which you cannot solve with classical resources. That's the idea behind. And of course, we know easy problems which we can easily calculate, but then the factorization is something which is very difficult to calculate because a classical machine needs to go through every single number to test whether it's a prime number, through every number, and this takes forever. So this is the basis of our current encryption techniques. And with a classical computer, you would need like 300 years to find solve the code or solve the decryption. But with Shor's algorithm, if you can do it, then you can do it in a few seconds. Shor, however, to solve Shor's algorithm needs quite some computational power because you also need error-free, fault-tolerant quantum computers. And this will still be quite some time. But in the meanwhile, we are interested very much in chemical applications, so calculating molecules. And you have seen the analogy between qubits and molecules, accelerating the discovery of new materials, also helping with machine learning and also optimization techniques, because in optimization, you typically also have an exponential increase of your problem with a number of parameters. And this is where quantum computers are very interesting. And there are lots of applications in the industries where these mathematical problems appear. So simulating nature, as I mentioned, physics, chemistry, material science, machine learning, factoring, ranking and symmetric groups, but also risk analysis, optimization, sampling problems. And they all have actually a different speed up factor. I'm not sure, you don't see it here, right? It's disappeared. No, here. There's an exponential speed up for these type of problems, a kind of a bit of a greater than polynomial speed up, and here quadratic speed up. That's also part of the research to get this done. But just an example, if you use, if you pick this example of nitrogenase or the ammoniac synthesis, which is one of the big important chemical processes in our world, because this is used to actually create fertilizer. And it consumes about 2 to 3% of so creating ammoniac consumes about 2 to 3% of the entire energy consumption of the earth. And we also know that, nitrogenase actually is an enzyme which can do this at room temperature, because here it's a Haber-Bosch-Verfahren where you need 400 to 500 degrees Celsius, 350 bars. It was invented in the 1900s. And it really consumes a lot of energy and also creates a lot of CO2. But nitrogenase, this enzyme, is able to do this at room temperature, but we don't really know how it works. In order to calculate this process, we would need about 135 qubits with a circuit depth of 10 to the 15th. Unfortunately, this is not yet possible, but this is the kind of problem we want to solve. And we, of course, work hard that we can really increase the circuit depths and increase the quality of the processing. So these are examples of calculations of, in this case, H2, or here, I think it was lithium hydride and boron dihydride. And you can do it here with a number of qubits. That's really not many qubits, and this was done in 2017, so it's many years back. But what I wanted to show is here that the solid line is the ideal line, because this you can still compute exactly by a HPC. And you see that the computation, the quantum computation at that point had some errors. And the errors came from decoherence, limited iterations of the number of calculations, sampling error, etc., etc. But when you do actually a trick, and I think I will come later to that, then you can actually come to the exact result. How this is done is actually with a variational quantum eigensolver, where you work with a classical computer and a quantum computer together, because you do actually the trial state preparation on the quantum computer, and then you do the optimization of the energy on the classical computer, and you do this in many iterations. And this is what costs a lot of time. Therefore, the architecture of your computer is very important to also reduce the time. So a big problem is the errors which we still have, because the errors are actually corrupt the computation, and the error probability per gate of best state of the art is in the range of 0.3. And this is something which need to be improved. And you can correct the error, which is today not possible because you need so many qubits in order to do it, or you can mitigate the error. And I still have a lot of work, a lot of material, but I actually would like to skip over all this material because otherwise it takes too long, and come to one recent paper which we actually just published 2 days ago. This is error correction. You can look into this. The big problem of error correction is that you cannot measure the qubit state and then correct it, because when you measure it, you destroy it. So you need a lot of other qubits around in order to detect the error of your qubit, the state of your qubit. So you have 25 data qubits in this example, and one encoded qubit, and 24 qubits are there to check the parity and figure out in which state the qubit is, to measure the phase and to measure the amplitude. And then of course you have to correct it. Right? First you have to identify it, and then you have to correct it. That's super complex, and it's today there's a lot of research going into it. What's the best way how to do it? And I don't want to go into it, but I will skip over it. There are many techniques which are still investigated, and there really needs to be more research to be done to figure out the right way. However, what I wanted to share with you in the end is that this is an important chart, because there is not only error correction, there is also error mitigation, which means, a bit simplified, if you know your error, you can mitigate for it. You can even kind of calculate it out. And the idea here is that you have here the problem complexity and the computation time. If you use it's a problem where a classical computer has an exponential increase in compute time when the complexity of the problem increases. A quantum computer could do this with just a really small increase in computational power with complexity of the problem. But it has this enormous additional number of qubits it needs to get started, because you need to error correct. So therefore, today we are kind of here that we can, we don't have a problem which a quantum computer can solve better than a quantum computer, because of this complexity which would need for the error correction. However, what we can do is actually quantum error mitigation. So we can mitigate the error. This needs, however, also an overhead. But we want to actually reach a regime, I want to show you in a minute that we are already there, where we can do error mitigation with more overhead, but less increase of resources compared to a classical computer. And this is an example which I would like to show you. And so the idea here is that we use zero noise extrapolation. This I showed you before. This is a compute which was done in 2017. We had these errors, but then actually we found a way of how to mitigate it with the zero noise extrapolation. How did it work? These are the microwave pulses you give to your qubits. Right, you have qubits 1, 2, 3, 4, and you give microwave pulses, you do a measurement, then you have an error. Now you actually intentionally increase the error by having broader pulses or higher amplitudes. And then you learn the error, you increase the error, you see how it reacts, and then you can actually, how do you call it? You can go to zero, extrapolate to zero error, and then you get your exact result. And we have demonstrated this technique the first time in 2019, where we could then show when we do 5 measurements, then we can actually achieve by this extrapolation the right result. So we have a bit more overhead because we have to, instead of 1 calculation, 5 calculations, but we can get the exact result. And this was done with, just a depth of 3 and a small, I think 4 qubits. And what we have done and demonstrated now and published actually 3 days before in Nature is that we can do this now with a 127 qubit chip and with a circuit depth at 60 actually. This is the first example where it was done with 36. And in this case, we do an Ising solver. So we have we look at here a trotterized time evolution of an Ising spin lattice. That's a Hamiltonian which we solve. And we use single qubit gates, RX gates as indicated here, and interleaved with so-called CC gates, which are shown here. And this is quite a complex circuit with quite a depth. And this type of physics has been recently also used to look into quantum many-body scars or time crystals or Majorana edge modes. And when we now look at the result, then as I mentioned, this 2017 result was done with 4 qubits and a depth of 2. And now we actually have done it with a depth with 127 qubits and a depth of 60. So this was 2017. Now we can do it for this quantum volume. And now, as I mentioned, the 127 qubit chip you can no longer simulate. So how do you know that you're right? Good question. So what we did is actually, in this case, we look at the, I think perhaps I can show it on the other one better. Here. We have actually at the Rx angle delta 0 and pi half, you can calculate it. Because there you are using Clifford gates. And Clifford gates you can easily calculate classically. So at a delta angle of 0 and pi half, you can calculate it exactly with a big HPC machine which needs to run a long time. And then when we show the unmitigated result, you see that it's very different to the mitigated result. And actually, what you see here, these are actually the ones which you can no longer also calculate in between, but you see at 0, at pi half, and at 0, the points are verified. And we have done the same actually for a calculation of 68 qubits here, where the HPC can still calculate it. So we have done it for different numbers of qubits and then verified it for the ones where the HPC can still calculate it, that the result of the HPC and the mitigated result are the same, and the unmitigated is completely different. So with this, we could for the first time actually demonstrate that a quantum computer has calculated something which a classical computer cannot calculate. And so with this noisy quantum computer, by using error mitigation, we can produce accurate expectation values, which are no longer achievable by classical results. And this we call, that's the evidence for utility of quantum advantage by using error mitigation, but not needing error correction, because there is still a bit of a path to go for error correction. And with this, I think I would like to stop. And these are some of the take-home messages of this latest result. And thank you very much for listening. And if there are further questions, I'm here. Thank you.
Thank you very much. Very exciting. And questions?
So,
Actually, I want to share. Actually, first, I want to share that there is actually a quantum hub in Poland. So the I don't know how to pronounce it. Poznan Supercomputing and Networking Center has access to our quantum computers, and since I think February this year, or no, last year actually, and are also already very active on it. And when you log into such a in your onto the screen, then you actually see all the different computers. You can pick them, you can calculate on them, and you can also get more information about on our quantum computing website. And I wanted to share, if you're interested to learn more, then there are also lots of further resources which you can make use of, like free access to lower number of qubit processors, special access actually for quantum computing for lectures, so also for academics. There are hackathons, there are summer schools, there are YouTube lectures, and there's also a Qiskit open textbook, which you can look and learn more about quantum computing, and also about Qiskit, which is an open source language to program quantum computers. And now I stop. Thank you.
So first question.
Right, no, my turn there. So on your roadmap for the quantum computing and progress there, do you have optical interconnects to coherent to
Yes. So we have like short interconnects, right? Because the 2-qubit gates you can only make if you have a very short distance. But we are actually also working in Zurich, and my team also on quantum transduction, which means we are working on devices to transduce from a microwave into a photon and vice versa.
Okay. Oh, and one more question. How about Majorana?
Yes, interesting topic. There is more to be done.
Okay, yeah, but it's no roadmap yet clearly there, right?
So we are studying really just the fundamental physics of it,
right.
Because there is, I mean, to my opinion, not really yet a Majorana true demonstration, which everyone
nobody's seen it yet,
believes, right?
Right.
And so building a qubit, I wouldn't say it, but we actually just want to understand what is the right route to look further, right?
Okay, thank you.
Oh, next question, please.
yes, so thank you very much for interesting talks. I have a few, actually. Okay, so I have with me.
Please use the microphone.
Okay. So yeah, I wanted to ask about the cooling. What do you use to cool the computer? Because few millikelvins is a quite low temperature, and I don't know if you use some kind of dilution refrigerator with. Yeah.
Yes, these are. I mean, So what we use in the lab are kind of dilution refrigerators. We are not. I mean, there is also some work where we look into building fridges, but we also collaborate with companies who are really experts on the cooling of fridges, right?
Okay,
so there's nothing special.
Okay. So, and the following question I have is, how is it optimal for you in terms of resources like costs of materials and scaling? Because you talked about scaling circuits, but what about this cooling system when you scale circuits?
Yes, and there is also on the internet also a video where you see how the system 2 looks like, right? Because we have now built system 1. But for the 1000-qubit chip, we need system 2 because we need the new lines coming in with the flex cables, and also it's a larger chip, so it needs a larger a cooling stage, etc. And so there's definitely also research and optimization going on in that area.
Thank you very much.
Actually, I have a question regarding the number of qubits, because they come in numbers like 133, 127, 433. Why?
The major reason is in principle this layout of the heavy hex layout which we're using.
Okay. And the prime number, these are prime numbers, right? Is it?
I mean, you've seen the, let me see whether I can quickly find it. Here. So it's really more this specific symmetry we are utilizing, because we are in the error correction regime. We are right now looking into the heavy hex code, because that's a very good trade-off between interconnectivity between qubits, which is important, but also the crosstalk which you may have between qubits. So this is trade-off why we chose this architecture.
Okay, thank you.
Thanks for very nice, interesting talk. I have several very naive questions. So when you have several hundred qubits here, it's physical qubits, not logical qubits.
These are all physical qubits. I touched a bit on the error correction. I did not have enough time to go into it. But
so how many logical qubits does it correspond to? Should I divide it by 25?
So that's again also it's not clear right now, because it depends on the gate fidelity you are able to achieve, and also on the error correction code you are using, and the interconnectivity you can achieve in your qubits. So the better they are connected with each other, the less qubits you need. The less physical qubits you need, the better your fidelity is, you less qubits you need. Therefore, we really want to reach also a high fidelity, because then you need less qubits. So the question of exactly this is a number is very difficult to give, because it depends very much on which error correction code you're using.
Okay, another naive question. So for several years, I heard that there are several platforms for realizing qubits, and there is no clear winner between these platforms. But what I see that almost all quantum processors, which were finally realized, are based on superconducting qubits.
They're actually also ion qubits. So also atoms. So when you look at, Google is also using superconducting qubits. So Rigetti uses superconducting qubits. There is IonQ, or also Alpine Quantum Technologies from Innsbruck, which are using ions.
But they have much less qubits.
Yes, so we have chosen this platform because it's intrinsically fast gate operation. And we believe also that the scalability of the qubits it's easier than compared to ions.
But what are the drawbacks of this platform compared to ions?
So the advantage of the ions is that you can achieve a very high interconnectivity in principle between the qubits.
So you can entangle
yes,
any
because you can
pair.
move them in and out. You can move the ions around with your electric field. And then you can achieve a kind of a arbitrary interconnectivity between the bits. But the problem is also it takes you a hell lot of time.
Okay.
So there are always advantages and disadvantages, and that's why we believe it's also very important that one looks at the benchmark parameters, and everyone kind of tries to fulfill these, or the best you can, these benchmark parameters, right? And then you will see who will win. And I always say, when you look at conductors, you also see the devices sometimes change, right? So things may also emerge with time, right? And when you look at, for example, to spin qubits today, they have still a high variability, but they would be also intrinsically fast. They can live at Kelvin. They have only two states because the spin has up and down, so you don't really have another level, right? So there are also advantages, but you cannot achieve them yet. Mm-hmm. So can we solve these challenges that we may be able to make them a nice platform? May the ion qubits people figure out how to scale their technologies? Maybe. But you have to, at a certain point you have to pick your horse.
Okay. If one more naive question.
We already lost our time advantage, but yeah, please, if it's quick, and then we will have the last one, and then we will close the session.
Okay. It's more theoretical kind of question. Why the quantum logic is limited only to 2 states? If it can go to, it can implement other higher states in the computation, and then naively, I would say it would allow more dense operations in principle.
So there are also other types of quantum computation. There are also like annealing. There are also states where you use more states, but that's even more complicated. And so I'm not the theorist who can explain you what, but there are papers and models where you can also use a higher number of states. But I think the complexity in the implementation does not get easier.
Team?
Hi, thank you very much for the nice presentation. I have a question about the Ising model results. So I didn't follow it in detail. Can you put it in context to the D-Wave work where they are doing the annealing with the Ising model?
So what we wanted to demonstrate here is the error mitigation, right? That we can achieve, and we use the Ising model as an example. So the key result here is, in principle, you have still noisy qubits, but within that 127 qubits and the depths of 60, we were able to achieve a result, a kind of an observable, a measure observable, which is not destroyed by noise.
Okay, and so the ability to make gates now allows you to do this mitigation, right? This is it.
Yes, and yes.
Thank you.
Okay, let's thank Heike once again.
Thank you.
So Heike unfortunately also cannot stay with us because of important meetings and putting this research forward, but she will stay with us tonight, this evening, so there is need to chat with her during the barbecue maybe, but please allow also for some food. And then I have one announcement.